You've been lied to. Not intentionally, perhaps, but lied to nonetheless. Every documentary you've watched, every science book you've read, every classroom lesson that painted the universe's birth as a cosmic explosion, they've all whispered the same beautiful deception into your willing ears. The Big Bang did not bang. Close your eyes for a moment. Picture the most explosive event you can imagine. Feel the shock wave. Hear the deafening roar. See the blinding flash of light tearing through darkness. Now multiply that by infinity. Compress it into a point smaller than the period at the end of this sentence, and let it birth everything that has ever existed, or ever will exist. This is the story we've been told. This is the lie that sounds like truth. But what if I told you that the moment of creation was silent? What if the birth of everything happened without sound, without explosion, without the dramatic cosmic fireworks we've been promised? What if the universe didn't explode into existence, but whispered itself into being, stretching like a cosmic exhale across dimensions we cannot fathom? You might wonder why this matters. You might think this is merely semantic. Explosion or expansion, bang or whisper. What difference does it make to your life on this spinning rock we call home? But here's the terrifying truth. If we've been wrong about how the universe began, what else have we been wrong about? If the very foundation of cosmology rests on a misconception, then every assumption we've built upon that foundation becomes suspect. Think about this. Every night when you look up at the stars, you're seeing light that has traveled for years, decades, centuries, millennia to reach your eyes. That light carries information, cosmic messages written in wavelengths of radiation, telling us stories about distant worlds and ancient events. But what if we've been reading these messages incorrectly? What if the universe has been trying to tell us something entirely different, and we've been too committed to our explosive origin story to listen? The word bang implies an event, something that happened at a specific moment, in a specific place, with a beginning, middle, and end. But space itself doesn't work that way. Space isn't a container that holds things. Space is the very fabric upon which existence is embroidered. When we say the Big Bang created space, we're making a statement so profound that most people never pause to consider its implications. We're saying that before this moment, there was nowhere for anything to exist. There was no stage upon which cosmic drama could unfold. But here's where the deception deepens. We cannot think about before the Big Bang, because time itself supposedly began with this event. The very concept of before becomes meaningless when time has no prior existence. Yet our human minds evolved to navigate cause and effect in a linear temporal framework. Rebel against this notion. We demand to know what came before, what caused the cause, what lit the fuse of cosmic creation. Consider the audacity of what cosmologists are asking you to accept, that everything you see, everything you are, everything that has ever mattered, emerged from nothing, nowhere, at no particular time, for no particular reason, and not only did it emerge, but it did so in perfect accordance with mathematical laws that themselves had no prior existence. The universe, in this telling, is both miraculous and accidental, both inevitable and impossible. You've been told that evidence supports this story. You've been shown redshift measurements, cosmic microwave background radiation, mathematical models predicting a singular moment of infinite density and temperature. But evidence can be interpreted in multiple ways. And the interpretation we've chosen reveals as much about our human psychology as it does about cosmic reality. What if the universe has no beginning? What if it has always existed in some form, cycling through phases we cannot comprehend, breathing in and out across timescales that make human history seem like a single heartbeat? What if what we call the Big Bang was merely the universe clearing its throat, preparing to speak truths we're only now beginning to hear? The silence of space should have been our first clue. In the vacuum between stars, sound cannot travel. There is no air to carry the compression waves we interpret as noise, the cosmic events we imagine as thunderous, the collision of galaxies, the death of stars, the birth of black holes, all happen in perfect, absolute silence. If the universe's birth was truly an explosion, it was the quietest explosion in history, unheard by anyone because there was no one to hear it, and nothing to carry the sound. But perhaps the universe doesn't need to make noise to make its point. Perhaps its very existence is statement enough. Every atom in your body was forged in the nuclear furnaces of ancient stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it cooked up in stellar cores and scattered across space when those stars died. You are literally made of star stuff, cosmic debris, given temporary consciousness, walking around on a planet made of the same stellar ash, under a sky filled with other stars, busy making more of the same. This is where the story becomes personal, where cosmic deception meets human truth. Whether the universe began with a bang or a whisper, whether it's finite or infinite, bounded or boundless, it created you somehow through processes we only dimly understand. The cosmos arranged itself in such a way that atoms learned to think, molecules learned to feel, and star stuff learned to wonder about its origins. You are the universe's way of examining itself. Your eyes are cosmic apertures through which space and time peer back at their own reflection. Your thoughts are the universe thinking about itself. Your questions about cosmic origins are the cosmos questioning its own existence. In a very real sense, when you ask whether space is endless or infinite, you are space asking whether it is endless or infinite. But here's the most unsettling possibility of all. What if the question itself is wrong? What if asking whether space is endless or infinite is like asking what color Wednesday is, or how much justice weighs, or where exactly imagination is located? What if we're applying concepts that work perfectly well in our human-scale experience to realms where those concepts have no meaning? The human brain evolved to navigate a world of medium-sized objects, moving at medium speeds across medium distances during medium spans of time. We developed intuitions about beginnings and endings, boundaries and centers, here and there, now and then. These intuitions served us well when avoiding predators and finding food. But they may be completely inadequate for understanding the nature of cosmic reality. Consider how we think about distance. On Earth, everything has a definite location relative to everything else. You can measure the distance between any 2 points, draw a map, create coordinates, establish reference frames. But what happens when you try to apply this thinking to the universe as a whole? Where is the center of everything? What are the cosmic coordinates of your current location? Distance from what? Location relative to what? The moment you try to step outside the universe to examine it from an external perspective, you realize the impossibility of the task. There is no outside. There is no external perspective. There is no cosmic map with "you are here" marked by a helpful arrow. The universe isn't located anywhere, because it is the very definition of everywhere. It doesn't exist in space and time. It is space and time. This is where language begins to fail us, where words become inadequate tools for describing reality. When we say the universe is expanding, expanding into what? When we say it has a beginning, beginning from what? When we say it might be infinite, infinite in relation to what finite reference point? Every word we use carries implicit assumptions about containers and contents, insides and outsides, beginnings and endings, assumptions that may be fundamentally inapplicable to cosmic reality. You've been taught to think of infinity as a very large number. But infinity isn't a number at all. It's a concept that breaks our mathematical intuitions and reveals the limitations of human thought. You can't count to infinity. You can't add one to infinity and get a larger infinity. You can't divide infinity in half and get two smaller infinities. Infinity doesn't behave like anything in our experience behaves. Yet, here we are, asking whether the universe might be infinite, applying this paradoxical concept to the totality of existence itself. What would it mean for space to be infinite? It would mean that no matter how far you traveled in any direction, there would always be more space ahead of you. It would mean that every possible arrangement of matter and energy exists somewhere, including perfect copies of you reading these words, making these same realizations, wondering about these same questions. In an infinite universe, everything that can happen must happen. Not once, but infinitely many times. There are infinite versions of Earth, infinite versions of your life, infinite variations on every moment you've ever experienced. Some versions are nearly identical to this one, differing by the position of a single atom. Others are radically different, playing out alternative histories where different choices led to different outcomes. But if the universe is infinite, then the word universe itself becomes problematic. Uni means one, singular, total. How can there be one totality if that totality contains infinite variations of itself? How can there be a single cosmos if that cosmos includes infinite alternate cosmoses? This is where the deception reveals its deeper layers. We've been thinking about these questions as if they have answers, as if the universe is the kind of thing that can be finite or infinite, bounded or boundless, singular or multiple. But what if reality transcends these categories entirely? What if the cosmos exists in ways that cannot be captured by human concepts, no matter how sophisticated those concepts become? Every night, when you lie in bed staring at the ceiling, you are staring through the Earth toward distant galaxies, racing away from you at incomprehensible speeds. The darkness above your head extends farther than light itself has had time to travel since the supposed beginning of everything. You are looking into deep time, into the cosmic past, into regions of space that may be forever beyond your reach. But here's what should keep you awake. The darkness isn't empty. It's full of space itself, space that may extend infinitely in all directions, space that may connect to other spaces you cannot imagine, space that may fold back on itself in dimensions your mind cannot visualize. The nothing between the stars isn't nothing at all. It's the fundamental substance of reality, the stage upon which all cosmic drama unfolds. And you are part of that drama. Your existence is not separate from cosmic existence. It is cosmic existence, temporarily organized into the pattern we call human consciousness. The space between your atoms is the same space that stretches between galaxies. The time flowing through your thoughts is the same time that governs the dance of planets and the death of stars. When you ask whether space is endless or infinite, you are asking about your own nature. When you wonder about cosmic boundaries, you are wondering about the boundaries of yourself. When you contemplate the universe's origin, you are contemplating your own deepest identity. The questions are personal because you are not merely in the universe. You are the universe, temporarily concentrated into a form capable of asking questions about itself. This is the final layer of deception, the illusion that cosmic questions are abstract, theoretical, disconnected from daily life. The truth is that cosmology is autobiography. The story of the universe is your story. The mystery of cosmic origins is the mystery of your own existence. Whether space is endless or infinite isn't just a scientific question. It's the most personal question you can ask. So as we begin this journey together, as we prepare to explore the deepest questions about reality itself, remember that you are not just learning about the universe. You are the universe learning about itself. You are space and time and matter and energy temporarily arranged into a pattern that can think and feel and wonder. You are the cosmos made conscious, and through your consciousness, the cosmos contemplates its own nature. The Big Bang did not bang. This much we know. But what did happen? What is happening? What will happen? These questions invite us into mysteries so profound that even asking them changes us. The universe is stranger than we imagine, and it may be stranger than we can imagine, but we are part of that strangeness, expressions of cosmic creativity so unlikely and wonderful that their very existence suggests realities beyond our current comprehension. You have been lied to, yes, but only because the truth is too vast for any single story to contain. The real deception isn't in the details of cosmological theories. It's in the assumption that reality can be captured by any theory at all. The universe is not a problem to be solved, but a mystery to be lived. And you, conscious arrangement of star stuff that you are living that mystery right now, in this moment, as you read these words and wonder about your place in the cosmic scheme. The journey we're about to take will challenge everything you think you know about space, time, existence itself. It will reveal contradictions that cannot be resolved, paradoxes that cannot be untangled, questions that lead only to deeper questions. But it will also reveal something more precious than answers. It will reveal the magnificent strangeness of being conscious in a universe that may itself be conscious in ways we cannot fathom. Are you ready to discover what lies beyond the lies we tell ourselves about cosmic reality? Are you prepared to venture into territories where human language breaks down and human concepts fail? Are you willing to embrace mysteries that may have no solutions, questions that may have no answers, truths that may be too large for any mind to contain? Then let us begin. Let us step together into the infinite darkness between certainties, into the endless space between what we know and what we need to know, into the boundless mystery of existence itself. The universe is waiting to tell you its secrets, not through words or theories or mathematical equations, but through the direct experience of being part of something so vast and strange that even beginning to understand it transforms you completely. You are about to discover that the question isn't whether space is endless or infinite. The question is whether you are ready to become infinite yourself, to expand your conception of reality beyond every boundary you've ever imagined, to embrace a vision of existence so profound that it changes not just what you know, but who you are. The cosmic story begins not with a bang, but with your willingness to listen to the silence between the stars, to hear the whisper of space itself as it tells you truths about your own deepest nature. The universe has been waiting billions of years for this moment, for you to become conscious enough to ask the right questions, brave enough to face the answers, and humble enough to accept that the greatest truths may lie forever beyond human comprehension. Welcome to the real story of everything that exists. Welcome to your own story, told on a cosmic scale. Welcome to the mystery of space and time and consciousness, the mystery that you are living, breathing, thinking proof that the universe is far stranger and more wonderful than we have dared to imagine. The mathematics are beautiful, elegant, seemingly perfect. They dance across blackboards in universities around the world, equations that claim to describe the birth and evolution of everything that exists. E equals mc squared. The Friedmann equations, Einstein's field equations relating space-time curvature to matter and energy. Each symbol precisely placed, each relationship carefully derived, each conclusion seemingly inevitable. But mathematics, for all its beauty, is just a language. And like any language, it can lie by telling truths that miss the deeper reality. You've been shown the evidence, and it appears overwhelming. Edwin Hubble peered through his telescope in 1929 and discovered that distant galaxies are racing away from us. Their light stretched toward the red end of the spectrum like cosmic sirens fleeing into the night. The farther away a galaxy lies, the faster it retreats, as if the entire universe is expanding uniformly in all directions. This observation became the cornerstone of modern cosmology, the foundation upon which we built our story of cosmic inflation and universal expansion. But here's what they don't tell you in those introductory astronomy courses. Hubble himself never fully accepted the interpretation of his own discovery. He suspected that redshift might have causes beyond simple recession velocity, that the universe might be more complex than his observations seemed to suggest. He spent the rest of his life searching for alternative explanations, uncomfortable with the cosmic implications of his own revolutionary measurements. The man who gave us our expanding universe died uncertain about whether the universe was actually expanding at all. Picture the cosmic microwave background radiation, that faint afterglow of creation that permeates every cubic centimeter of space. It whispers to us from the edges of the observable universe, carrying information about the cosmos when it was only 380,000 years old, a cosmic infant by current standards. This radiation appears remarkably uniform across the sky, with tiny fluctuations that supposedly seed the formation of galaxies and galaxy clusters. Scientists call it the most perfect blackbody spectrum ever observed, a thermal fingerprint of the universe's fiery youth. Yet even this seemingly definitive evidence carries troubling implications. The cosmic microwave background appears the same in all directions, suggesting that widely separated regions of the early universe had somehow achieved thermal equilibrium, despite being too far apart for light to travel between them. This is called the horizon problem, and it suggests that our current understanding of cosmic history contains fundamental gaps. How did distant regions of space coordinate their temperatures without any possibility of communication? How did the universe achieve such remarkable uniformity across scales that should have been completely disconnected? The solution proposed by cosmologists is cosmic inflation, a period of exponential expansion that supposedly occurred in the first fraction of a second after the Big Bang, stretching tiny quantum fluctuations to cosmic scales and smoothing out irregularities in the process. But inflation itself raises more questions than it answers. What caused inflation to begin? What caused it to stop? Why did it happen exactly when it did, and not earlier or later? The inflation field that drives this process has never been directly observed. Its properties remain largely theoretical, and its very existence depends on physics beyond our current understanding. Consider what cosmic inflation actually proposes: that in less than a trillionth of a trillionth of a trillionth of a second, the universe grew from smaller than a proton to larger than a grapefruit, stretching space-time itself at speeds far exceeding the velocity of light. During this brief moment, the fundamental forces of nature supposedly separated from their unified state, matter and antimatter, somehow avoided mutual annihilation, and the basic structure of physical reality crystallized into the forms we observe today. All of this occurred before the universe was old enough for a single photon to cross the distance of a proton. The early universe wasn't just hot. It was a furnace where time itself was still learning to move, where space was so compressed that quantum mechanical effects dominated over classical physics, where the very concepts of here and there, now and then, had not yet achieved stable meaning. Temperature measurements become meaningless when matter itself exists only as a seething plasma of elementary particles, when electrons cannot bind to atomic nuclei because thermal energy instantly tears them apart again. Imagine trying to describe the color blue to someone who has never seen color, or explaining the concept of silence to someone who has never heard sound. This is the challenge faced by cosmologists attempting to describe the first moments of cosmic history. They must use concepts developed for our current universe, concepts like temperature, density, pressure, expansion, to describe states of reality where those concepts may not apply. They must employ mathematics derived from human experience to map territories that transcend all human experience. The density of the early universe supposedly reached values that make the cores of neutron stars seem like empty space by comparison. Matter was compressed to states where normal physics breaks down completely, where general relativity itself becomes inadequate, where quantum effects should dominate but quantum mechanics offers no clear guidance. At these extreme conditions, space-time itself becomes quantum mechanical, fluctuating and uncertain, possibly spawning baby universes or connecting to parallel realities through mechanisms we cannot fathom. But here's where the cosmic setup reveals its deepest mystery. If the universe has no edge, then where does it begin? If space itself is expanding, what is it expanding into? These aren't just philosophical puzzles. They're fundamental problems that challenge our basic understanding of existence itself. When we say the universe is expanding, we're making a theoretical assumption about the nature of space that may be completely wrong. Consider the balloon analogy often used to explain cosmic expansion. Scientists tell us to imagine the universe as the surface of a balloon being inflated, with galaxies represented as dots on the balloon's surface. As the balloon expands, the dots move farther apart, just as galaxies recede from each other in our expanding universe. But this analogy reveals more than it explains. It requires an external space for the balloon to expand into, an outside observer to watch the inflation process, a higher dimensional reality within which cosmic expansion can occur. The balloon analogy works only if we assume that our three-dimensional universe is embedded in a higher dimensional space, just as the two-dimensional surface of a balloon exists within three-dimensional space. But cosmologists insist that no such higher dimensional embedding is necessary, that space can expand without expanding into anything. They claim that expansion is an intrinsic property of space-time itself, requiring no external container or reference frame. Yet this explanation feels like semantic sleight of hand, using mathematical formalism to obscure conceptual mysteries rather than resolve them. What does it mean for space itself to expand? Space isn't a material substance that can stretch like rubber or flow like water. Space is the stage upon which all physical processes unfold, the framework within which matter and energy interact, the coordinate system that allows us to distinguish here from there. But if space is expanding, then what serves as the reference frame for measuring that expansion? How can we detect the growth of the very measuring stick we use to detect growth? The cosmic microwave background provides our most direct observational window into the early universe. But that window reveals a cosmos that seems too organized, too uniform, too precisely tuned to have emerged from the chaotic conditions supposedly present at cosmic birth. The temperature variations in this ancient light are incredibly small, just a few parts in 100,000. Yet these tiny fluctuations supposedly grew through gravitational amplification to create all the large-scale structure we observe today. But gravitational amplification takes time, and the early universe may not have provided enough time for such organization to emerge. If we trace cosmic history backward, using our current models, we encounter what cosmologists call the flatness problem. The universe today appears to be balanced on a knife's edge between expansion and collapse, neither curving back on itself nor flying apart indefinitely. For the universe to achieve this precise balance today, its initial conditions would have had to be fine-tuned to extraordinary precision. 1 part in 10 to the 60th power, a level of accuracy that makes winning the lottery every day for 1,000,000 years seem probable by comparison. This fine-tuning extends beyond cosmic geometry to the fundamental constants of nature themselves. The strength of gravity, the mass of the electron, the charge of the proton, the speed of light. All of these parameters appear to be adjusted with impossible precision to allow for the existence of stars, planets, and life itself. Change any of these constants by even a tiny amount, and the universe becomes hostile to complexity, unable to form atoms, unable to ignite nuclear fusion in stellar cores, unable to support the chemical processes that make life possible. Some cosmologists respond to this fine-tuning problem by proposing the existence of multiple universes, a multiverse where every possible combination of physical constants is realized somewhere, where our universe appears fine-tuned only because we exist within the tiny subset of universes capable of supporting observers. But the multiverse hypothesis, while mathematically appealing, cannot be tested or verified through any conceivable observation. It requires us to believe in the existence of infinite unobservable realities to explain the properties of the one reality we can observe. The mathematics of cosmic expansion assumes that the universe is homogeneous and isotropic on large scales, the same everywhere and in every direction. This assumption, known as the cosmological principle, simplifies the equations enormously and makes cosmic modeling mathematically tractable. But recent observations suggest that the universe may not be as uniform as we assumed. Galaxy surveys reveal enormous structures, cosmic webs, supervoids, galactic filaments stretching across billions of light-years that challenge our assumptions about cosmic homogeneity. These large-scale structures appear to be organized in patterns that our current models struggle to explain. The cosmic web resembles a vast neural network, with galaxies clustered along filaments separated by enormous voids that contain almost no visible matter. Some of these structures are so large that light hasn't had enough time since the Big Bang to cross them, yet they appear to be coherently organized across their entire extent. How did such coordination emerge without sufficient time for causal communication? Dark matter complicates the cosmic picture even further. This mysterious substance supposedly outweighs ordinary matter by a factor of 5 to 1. Yet it interacts with light and ordinary matter only through gravitational effects. We cannot see dark matter directly, cannot touch it, cannot capture it in any detector we've built. Its existence is inferred entirely from its gravitational influence on visible matter, the way galaxies rotate, the way galaxy clusters move, the way light bends around massive objects. But what if dark matter doesn't exist at all? What if the gravitational effects we attribute to dark matter result from modifications to gravity itself on cosmic scales? Several alternative theories propose that Einstein's general relativity breaks down when applied to the largest structures in the universe, requiring corrections that could eliminate the need for dark matter entirely. These theories face significant challenges, but so does dark matter. Despite decades of searching, no dark matter particle has ever been directly detected. Dark energy presents an even deeper mystery. This hypothetical form of energy supposedly comprises roughly 70% of the universe's total mass energy budget, yet it reveals itself only through its effect on cosmic expansion. Observations of distant supernovae suggest that cosmic expansion is accelerating rather than slowing down, as if some mysterious force is pushing space apart with ever-increasing strength. Dark energy provides the simplest explanation for this acceleration, but nobody knows what dark energy actually is or why it has the properties it appears to have. The amount of dark energy required to explain cosmic acceleration corresponds to a vacuum energy density that is smaller than quantum mechanical predictions by a factor of 10 to the 120th power, the largest discrepancy between theory and observation in the history of science. This cosmological constant problem suggests that our understanding of either quantum mechanics or general relativity contains fundamental errors, or that reality operates according to principles we haven't discovered yet. Consider the implications. We live in a universe where 95% of the total mass energy consists of substances we cannot observe directly, understand theoretically, or detect experimentally. Dark matter and dark energy are cosmic placeholders, mathematical constructs invented to make our observations fit our theories. They may represent genuine physical realities, or they may be symptoms of deeper problems with our theoretical framework itself. The cosmic microwave background, that supposedly pristine record of the early universe, contains anomalies that cosmologists struggle to explain. The famous axis of evil, a mysterious alignment of temperature fluctuations that appears to point toward specific locations in space, challenges the assumption that the universe looks the same in all directions. Other anomalies include cold, spots that are larger than they should be, correlations between distant regions that should be statistically independent, and asymmetries that suggest the universe may have a preferred direction or orientation. These anomalies might be statistical, flukes, instrumental artifacts, or signs of new physics beyond our current understanding. But they serve as reminders that even our best observational evidence contains mysteries that don't fit neatly into our theoretical frameworks. The cosmic microwave background may be telling us stories about the early universe that we don't yet know how to read. Time itself becomes problematic when we examine cosmic origins. If the Big Bang represents the beginning of time, then asking what happened before the Big Bang becomes as meaningless as asking what lies north of the North Pole. Yet human intuition rebels against the notion of temporal beginning. We demand to know what caused the cause, what initiated the initial conditions, what set the cosmic clock ticking in the first place. Some cosmologists propose that time is cyclical, that our universe is just one phase in an eternal cycle of expansion and contraction, creation, and destruction. Others suggest that time itself is emergent, arising from more fundamental timeless processes that operate according to principles we cannot yet comprehend. Still others argue that time may be quantized, composed of discrete units so small that the very concept of continuous temporal flow becomes an approximation valid only at macroscopic scales. The quantum mechanical nature of reality adds another layer of mystery to cosmic origins. If the early universe was small enough for quantum effects to dominate, then its properties should be described by probability distributions rather than definite values. The cosmic wave function, the quantum mechanical description of the entire universe's state, may exist in a superposition of multiple possibilities until observation collapses it into a single reality. But who or what serves as the observer of the cosmic wave function? In laboratory quantum mechanics, measurement by external observers causes wave function collapse, but the universe has no external observers. Some interpretations of quantum mechanics suggest that consciousness itself plays a fundamental role in determining physical reality, that the universe exists in a superposition of all possible states until conscious observers force it to choose specific outcomes through the act of observation. This leads to the participatory universe hypothesis, the idea that observers don't simply discover cosmic history, but actually participate in creating it through their observations. In this view, the questions we ask about the universe determine which aspects of reality become definite, which possibilities collapse from quantum superposition into classical certainty. The cosmic past may not be fixed until we observe it, measure it, think about it in specific ways that force reality to crystallize into particular forms. Consider how strange this makes our cosmic investigations. When we observe the cosmic microwave background, we may not be simply discovering what the early universe was like. We may be participating in determining what the early universe was like. Our telescopes become time machines that reach backward to influence the very events they observe, creating a cosmic feedback loop between present observation and past reality. The horizon problem returns with deeper implications when viewed through quantum mechanical lenses. If widely separated regions of the early universe achieved thermal equilibrium without causal contact, perhaps they were quantum mechanically entangled, sharing information through non-local correlations that transcend the speed of light. Quantum entanglement allows particles to remain correlated across arbitrary distances, changing state instantaneously when their entangled partners are measured, regardless of the spatial separation between them. Could the entire observable universe have emerged from a single quantum mechanical system with all regions remaining entangled despite cosmic expansion pulling them apart? If so, then the apparent uniformity of the cosmic microwave background might reflect quantum correlations, rather than thermal equilibrium, non-local quantum information sharing, rather than classical causal contact. The universe might be fundamentally holistic, with every part containing information about every other part, despite the apparent separation imposed by expanding space-time. But quantum entanglement itself raises profound questions about the nature of space and locality. If entangled particles can influence each other instantaneously across cosmic distances, what does this tell us about the fundamental structure of space-time? Perhaps space is not as fundamental as we assume. Perhaps distance and separation are emergent properties of a deeper non-spatial reality. Perhaps the entire notion of cosmic expansion rests on misconceptions about the nature of space itself. String theory and its extensions suggest that the familiar three dimensions of space may be projections or shadows of higher dimensional realities containing up to 11 dimensions or more. In these higher dimensional spaces, regions that appear widely separated in our three-dimensional slice might actually be close neighbors, connected by paths through extra dimensions we cannot perceive. What appears as vast cosmic distances might be artifacts of our limited dimensional perspective, like shadows on a wall that seem far apart while the objects casting them nearly touch. The cosmic setup reveals itself as more mysterious the deeper we probe. Every answer generates new questions. Every explanation requires new assumptions. Every solution creates new problems. The mathematics remains beautiful. The observations continue to accumulate. But the underlying reality seems to slip further away from our grasp with each new discovery. We find ourselves in the strange position of living within a universe we cannot fully understand, composed mostly of substances we cannot detect, operating according to principles we cannot verify, possibly embedded in higher dimensional realities we cannot perceive. The cosmic story we tell ourselves may be elaborate mythology rather than scientific truth, a narrative that comforts us with the illusion of understanding, while the real universe operates according to logic so alien that we mistake it for mystery. Yet, here we are, conscious beings capable of asking these questions, products of a cosmic evolution that somehow generated complexity, capable of contemplating its own origins. The universe has become aware of itself through us. Cosmic matter organized into patterns that can think and wonder and probe the deepest mysteries of existence. Whether we understand the cosmos correctly or not, we remain its most remarkable, known products, temporary arrangements of star stuff that have learned to question their own nature and the nature of everything that exists. The stage is set, but the stage itself may be far stranger than any drama we imagine unfolding upon it. Space and time, matter and energy, cause and effect, all the basic categories through which we interpret reality, may be inadequate for comprehending the cosmic truth. We are about to embark on a journey that will challenge not just our theories about the universe, but our fundamental assumptions about the nature of existence itself. The singularity waits at the heart of every black hole like a cosmic secret, too dangerous to whisper. It's a place where mathematics breaks down, where the equations that govern everything else in the universe surrender to infinities that have no meaning. Space curves back on itself until curvature becomes meaningless. Time stretches toward an end that never arrives. Matter compresses to infinite density while occupying zero volume, a physical contradiction that suggests either our physics is fundamentally wrong or reality itself contains paradoxes that cannot be resolved. You might imagine a singularity as an incredibly small, incredibly dense object, but this misses the profound strangeness of what cosmologists are actually proposing. A singularity isn't an object at all. It's a breakdown in the very concept of objecthood. It's the place where the question, "What is it?" stops making sense, where the categories we use to describe reality, size, shape, composition, location, become inapplicable. It's not that we don't know what's inside a singularity. It's that the concept of inside loses all meaning when space-time itself ceases to exist in any recognizable form. But here's what should keep you awake at night. If our universe began with a Big Bang singularity, then everything that exists, including you, emerged from this zone of cosmic meaninglessness. Your atoms, your thoughts, your capacity to wonder about cosmic origins, all of it supposedly crystallized out of a state where physics provides no guidance and mathematics offers no answers. We are asking you to believe that the most ordered, law-abiding, mathematically precise universe imaginable emerged from a condition of absolute disorder, infinite chaos, complete lawlessness. The mathematics that describe singularities are beautiful in their terror. Einstein's field equations, which work flawlessly everywhere else in the cosmos, generate infinities when applied to these extreme conditions. Division by zero appears in the denominators. Physical quantities become undefined. The mathematical machinery that successfully predicted the existence of black holes, gravitational waves, and cosmic expansion simply stops working when we try to peer into the singularity's heart. Physicists respond to this mathematical breakdown with a mixture of humility and denial. Some argue that singularities represent the limits of physical theory rather than genuine features of reality, that quantum mechanics must intervene at some scale to prevent the formation of true mathematical infinities. Others suggest that singularities are windows into new physics, regions where our current understanding gives way to deeper principles we haven't discovered yet. Still others propose that singularities are artifacts of classical general relativity, problems that will disappear when we develop a proper quantum theory of gravity. But quantum mechanics brings its own mysteries to the cosmic theater. On the deepest level, reality appears to be fundamentally probabilistic rather than deterministic. Particles don't have definite positions or velocities until they're measured. Physical systems exist in superpositions of multiple states simultaneously. The act of observation somehow forces nature to choose specific outcomes from a range of quantum possibilities. These aren't just technical details about subatomic behavior, they're statements about the fundamental nature of existence itself. Consider what quantum mechanics implies about cosmic history. If the early universe was small enough for quantum effects to dominate, then cosmic evolution should be described by probability waves rather than definite trajectories. The universe didn't follow a single path from Big Bang to present. It explored all possible paths simultaneously, existing in a cosmic superposition until something caused it to collapse into the specific reality we observe today. This is where the many worlds interpretation enters the cosmic drama. First proposed by physicist Hugh Everett in 1957, this radical interpretation suggests that quantum superpositions never actually collapse. Instead, reality continuously branches into parallel universes corresponding to every possible quantum outcome. When you measure a particle's spin and find it pointing up, there's another branch of reality where you measure it pointing down. Both measurements are equally real, but they occur in parallel universes that can no longer communicate with each other. Applied to cosmology, the many worlds interpretation suggests that our universe is just one branch of an infinitely branching cosmic tree. Every quantum event that occurred during cosmic evolution spawned new universes exploring alternative possibilities. There are universes where stars formed earlier, universes where galaxies never condensed, universes where the fundamental constants took slightly different values, universes where you made different choices about what to read this morning. The cosmic wave function, the quantum mechanical description of the entire universe's state, becomes a vast probability distribution encompassing all possible cosmic histories. We experience only one branch of this distribution, but the other branches are equally real, equally physical, equally deserving of the title universe. Reality becomes an infinite garden of forking paths, with consciousness somehow carving specific trajectories through the quantum multiverse. But this raises the profound question of cosmic consciousness itself. In standard quantum mechanics, observation by conscious beings appears to play a special role in determining which quantum possibilities become actual. The measurement problem, the question of how and when quantum superpositions collapse into definite states, remains one of the deepest unsolved puzzles in physics. Some interpretations suggest that consciousness is fundamental to physical reality, that the universe exists in quantum limbo until conscious observers force it to crystallize into specific forms. Imagine reality as a film reel where every possible moment already exists, stretched across the dimensions of space-time like frames in an eternal movie. From this perspective, time doesn't flow. It simply is. Past, present, and future coexist as different regions of a four-dimensional block universe. Your birth, your death, this moment of reading, and every moment in between exist simultaneously in the eternal now of space-time. The flow of time becomes a subjective illusion created by the way consciousness moves through this static, temporal landscape. This block universe picture, which emerges naturally from Einstein's relativity, challenges our deepest intuitions about causation and free will. If all moments exist equally, then the future is already real, already determined, already out there, waiting for consciousness to discover it. Your choices tomorrow exist as definitely as your memories of yesterday. The entire cosmic drama, from Big Bang to heat death, plays out in the eternal theater of space-time like a movie that's already been filmed. But quantum mechanics complicates this picture by introducing fundamental randomness into physical processes. If quantum events are truly random rather than merely unpredictable, then the future cannot be completely determined by the present. The block universe must accommodate genuine novelty, real creativity, authentic choice. Perhaps space-time resembles a growing crystal, with new moments crystallizing out of quantum possibilities at the advancing edge of time. Perhaps consciousness plays a role in this crystallization process, helping to determine which quantum possibilities become actual through the exercise of choice and observation. The anthropic principle enters here as both explanation and mystery. We find ourselves in a universe that appears finely tuned for our existence. Physical constants precisely adjusted to allow stars to burn, planets to form, life to evolve, consciousness to emerge. The probability of such fine-tuning occurring by chance appears vanishingly small. This leads to three possible conclusions. Either we're incredibly lucky, the universe was designed by some cosmic intelligence, or there are many universes with different properties, and we naturally find ourselves in one capable of supporting observers. The multiverse hypothesis extends this anthropic reasoning to cosmic scales. If quantum mechanics generates infinite parallel universes, or if cosmic inflation creates infinite separate regions of space with different physical properties, then the apparent fine-tuning of our universe becomes a selection effect rather than a cosmic coincidence. We observe fine-tuning because we exist. We couldn't find ourselves in any universe that wasn't tuned for our existence. But the multiverse remains frustratingly unobservable. By definition, parallel universes created by quantum branching cannot communicate with each other after the branching occurs. Separate cosmic regions created by inflation lie beyond our observable horizon, their properties forever hidden from our measurements. The multiverse explains cosmic fine-tuning at the cost of making that explanation untestable, unverifiable, scientifically sterile. This leads to deeper questions about the nature of scientific explanation itself. Is it sufficient for a theory to explain observations if that theory cannot be tested? Does the multiverse represent genuine scientific progress or elaborate metaphysical speculation dressed in mathematical clothing? Are we approaching the limits of what science can meaningfully address, or are we on the verge of breakthrough insights that will revolutionize our understanding of reality? String theory promises such revolutionary insights while delivering frustrating ambiguities. This attempt to unify quantum mechanics with general relativity requires reality to possess up to 11 dimensions, most of which remain hidden from a direct observation. In these higher dimensional spaces, the familiar particles and forces of physics become vibrations of tiny strings oscillating at frequencies beyond our ability to detect. The mathematics of string theory is incredibly rich and elegant, but it makes few testable predictions about observable phenomena. The extra dimensions of string theory might be compactified, rolled up so small that they're invisible at macroscopic scales, or they might extend to cosmic distances while remaining hidden from our three-dimensional perspective. These hidden dimensions could harbor entire landscapes of possible physics, with different regions supporting different physical laws, different constants, different possibilities for matter and energy to organize themselves into complex structures. Consider the implications. What we call the universe, this vast expanse of galaxies, stars, and planets that we can observe, might be just a three-dimensional shadow cast by higher-dimensional reality. The cosmic drama we think we're observing might be a severely limited perspective on processes occurring in spaces we cannot perceive, dimensions we cannot access, realities we cannot imagine. Loop quantum gravity offers an alternative approach to quantum spacetime, suggesting that space and time themselves are quantized, composed of discrete units so small that the very concept of smooth continuity becomes an approximation. At the Planck scale, roughly 10 to 135 meters, spacetime might resemble a foam of quantum fluctuations rather than the smooth manifold described by general relativity. Space might consist of individual units of volume. Time might flow in discrete ticks rather than continuous streams. If space-time is quantized, then the Big Bang singularity might not represent a true beginning, but rather a quantum bounce, a transition from a previous contracting phase to our current expanding phase. The universe might be eternal, cycling through phases of expansion and contraction driven by quantum gravitational effects that become dominant at extreme densities. Our Big Bang might be just the most recent cosmic heartbeat in an eternal rhythm of creation and destruction. The cosmic microwave background takes on new significance in this context. If the universe underwent a quantum bounce rather than emerging from a true singularity, then the patterns we observe in ancient light might carry information from before the Big Bang. Fossil evidence of previous cosmic cycles, quantum mechanical scars left by earlier phases of cosmic evolution. We might be reading cosmic history incorrectly, interpreting evidence of cosmic recycling as evidence of cosmic birth. Eternal inflation complicates the picture further by suggesting that cosmic expansion is not a temporary phase, but an eternal process. In this scenario, Big Bang events occur continuously throughout an ever-expanding multiverse, creating bubble universes like ours embedded in a larger inflating space, like raisins in an infinitely growing loaf of bread. Our observable universe becomes just one bubble among infinitely many, each with potentially different physics, different constants, different possibilities for complexity and consciousness to emerge. The mathematics of eternal inflation suggest that this process has no beginning and will have no end. The multiverse grows without limit, spawning new bubble universes at an ever-increasing rate, exploring every possible variation of physical law through an infinite cosmic experiment. Our universe, with its specific properties and evolutionary history, occurs infinitely many times throughout this inflating multiverse, along with infinitely many variations on every possible theme. But eternal inflation raises profound questions about probability and meaning in an infinite multiverse. If every possible universe exists infinitely many times, then all possible observations occur with equal frequency. The probability of any particular measurement becomes undefined, meaningless, impossible to calculate, the very concept of scientific prediction breaks down when all possibilities occur infinitely often. This is the measure problem, the question of how to assign meaningful probabilities to events in an infinite multiverse. Different approaches to this problem yield different answers about the likelihood of various cosmic scenarios. Some suggest that we're more likely to be Boltzmann brains, random quantum fluctuations that briefly organize into conscious observers. Then, biological creatures evolved through cosmic history. Others argue that selection effects favor universes with specific properties that we haven't identified yet. The holographic principle emerges from attempts to understand black hole thermodynamics and the information paradox. This principle suggests that all the information contained within a volume of space can be encoded on its boundary, like a hologram where three-dimensional images emerge from two-dimensional surfaces. Applied to the entire universe, holography implies that everything we perceive as three-dimensional reality might actually be information encoded on a distant two-dimensional boundary. Imagine discovering that your entire life, including your thoughts about cosmic mysteries, is actually a holographic projection from information stored on the cosmic horizon, the boundary of the observable universe. The stars, planets, galaxies, and even your own body might be emergent patterns in a vast cosmic hologram, three-dimensional shadows cast by two-dimensional information processing occurring at scales we cannot comprehend. The AD-SCFT correspondence provides a concrete example of holographic duality, demonstrating that certain gravitational theories in higher dimensional spaces are mathematically equivalent to quantum field theories on their lower dimensional boundaries. This correspondence suggests deep connections between gravity and quantum mechanics, between space-time geometry and information processing, between the physics of black holes and the quantum mechanics of elementary particles. But holography challenges our most basic assumptions about the nature of space and locality. If three-dimensional reality emerges from two-dimensional information, then the familiar concepts of distance, separation, and location become secondary properties rather than fundamental features of reality. The space between your atoms might be no more fundamental than the space between pixels on a computer screen, a useful illusion created by underlying information processing rather than a basic aspect of physical reality. Black holes themselves become laboratories for exploring these radical ideas. When matter falls into a black hole, it appears to freeze at the event horizon from the perspective of outside observers, while from the falling matter's perspective, it passes through the horizon and continues toward the central singularity. These conflicting descriptions of the same event, called the black hole information paradox, suggest that our understanding of space, time, and information contains fundamental inconsistencies. Recent work on black hole complementarity and the firewall paradox reveals even deeper puzzles. If black holes preserve information as required by quantum mechanics, then the event horizon might not be the smooth, empty boundary described by general relativity. Instead, it might be a wall of fire that destroys anything attempting to cross it. But this conflicts with the equivalence principle, which requires that freely falling observers experience nothing special when crossing the horizon. These paradoxes aren't just technical problems for theoretical physicists, they're cracks in our understanding of reality itself. They suggest that space, time, matter, and information might be related in ways that transcend our current conceptual frameworks. The universe might be far stranger than we imagine, organized according to principles that challenge our deepest assumptions about the nature of existence. Wormholes, hypothetical tunnels through space-time that connect distant regions of the universe, provide another window into cosmic strangeness. If wormholes exist, they could link different parts of our universe, different points in cosmic history, or even different universes entirely. Space and time would become multiply connected, riddled with shortcuts that make distant places and times accessible through hidden geometric relationships. The mathematics of general relativity allows for wormhole solutions, but keeping them open appears to require exotic matter with negative energy density, material that may not exist in nature. Some speculations suggest that quantum fluctuations might stabilize microscopic wormholes, creating a foam of space-time connections at the smallest scales. If so, then reality at the Planck scale might resemble a sponge rather than smooth manifold, honeycombed with quantum tunnels that connect every point to every other point through higher dimensional pathways. Imagine the implications. Every event in cosmic history might be connected to every other event through quantum wormhole networks. Information, causation, and correlation might propagate through these hidden channels faster than light can travel through ordinary space. The universe might be far more connected, far more integrated, far more holistic than appearances suggest. The apparent separation between distant galaxies might be an illusion created by our limited three-dimensional perspective on multiply-connected space-time. Dark energy enters this cosmic theater as perhaps the deepest mystery of all. Observations of distant supernovae suggest that cosmic expansion is accelerating rather than slowing down, driven by some form of energy that fills empty space and pushes it apart with ever-increasing strength. This dark energy comprises roughly 70% of the universe's total energy budget, yet we have no idea what it actually is or why it has the properties it appears to have. The simplest candidate for dark energy is the cosmological constant, a form of energy inherent in space itself, constant in both space and time, unchanging as the universe expands. Einstein originally introduced the cosmological constant to allow for a static universe, then abandoned it when Hubble discovered cosmic expansion. Now it returns as a potential explanation for cosmic acceleration, but its observed value creates one of the most severe fine-tuning problems in physics. Quantum field theory predicts that empty space should be filled with virtual particles continuously popping in and out of existence, contributing to vacuum energy density. But the predicted value of this vacuum energy exceeds the observed dark energy density by a factor of 10 to the 120, the largest discrepancy between theory and observation in the history of science. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels the vacuum energy contribution to extraordinary precision. Alternative explanations for dark energy include quintessence, a dynamic scalar field that changes over cosmic time, and modifications to gravity itself on cosmic scales. Perhaps Einstein's general relativity breaks down when applied to the largest structures in the universe, requiring corrections that naturally produce cosmic acceleration without invoking mysterious forms of energy. Perhaps dark energy isn't energy at all, but rather a symptom of our incomplete understanding of space-time geometry. The coincidence problem adds another layer of mystery. Why is dark energy beginning to dominate cosmic evolution just now? During the epoch when intelligent life happens to exist? For most of cosmic history, matter and radiation dominated over dark energy. In the far future, dark energy will dominate completely, driving cosmic acceleration until galaxies disappear beyond the cosmic horizon. We happen to live during the brief transition period when these different components of cosmic energy are comparable in magnitude. This timing could be pure coincidence, or it could reflect deeper connections between cosmic evolution and the emergence of consciousness. Perhaps universes that don't undergo this particular sequence of energy domination cannot support the long-term stable environments required for complex life to evolve. Perhaps the existence of observers is correlated with specific phases of cosmic evolution in ways we don't understand yet. Dark matter presents equally profound puzzles. This invisible substance supposedly outweighs ordinary matter by 5 to 1. Yet it interacts with light and ordinary matter only through gravitational effects. Decades of searching have failed to detect dark matter particles directly, despite increasingly sophisticated experiments designed to capture them. We infer dark matter's existence from its gravitational influence on galaxy rotation curves, galaxy clusters, and large-scale structure formation, but we have no direct evidence for its particle nature. Perhaps dark matter consists of primordial black holes, compact objects formed in the early universe before stars began to shine. These ancient black holes could populate galactic halos without producing detectable light, providing the gravitational scaffolding needed for galaxy formation while remaining invisible to our telescopes. But primordial black holes face their own theoretical challenges and observational constraints. Alternatively, dark matter might not exist at all. Modified theories of gravity like modified Newtonian dynamics, attempt to explain galactic rotation curves by changing the laws of gravity rather than invoking invisible matter. These theories face significant challenges in explaining all dark matter phenomena, but they remain viable alternatives that could revolutionize our understanding of space-time and gravitation. The possibility that both dark matter and dark energy are illusions, artifacts of our incomplete understanding of gravity, would fundamentally transform cosmology. Instead of a universe dominated by mysterious invisible substances, we would inhabit a cosmos where visible matter and energy interact. Through gravitational laws more complex than Einstein envisioned, the cosmic inventory would shift from 95% unknown to nearly 100% known, but only by revealing that the known physics of gravity requires radical revision. Cosmic inflation itself remains mysterious despite its central role in modern cosmology. The scalar field that supposedly drives inflation, the inflaton, has never been directly observed. Its properties remain largely unconstrained by observation. Different models of inflation make different predictions about cosmic structure formation, gravitational wave backgrounds, and the statistical properties of cosmic microwave background fluctuations. The horizon problem that inflation was designed to solve might have alternative explanations that don't require exponential expansion in the early universe. Pre-Big Bang cosmologies, ekpyrotic scenarios, and cyclic models all attempt to address cosmic homogeneity through different mechanisms. Some involve collisions between higher-dimensional branes. Others propose that our Big Bang was preceded by a contracting phase that established thermal equilibrium. Still others suggest that the horizon problem is an artifact of incorrect assumptions about initial conditions. The multiverse implications of eternal inflation remain hotly debated. If inflation produces infinitely many bubble universes with different physical properties, then the anthropic principle becomes a selection mechanism rather than evidence for cosmic design. We observe fine-tuning because we couldn't observe anything else. We necessarily find ourselves in a universe capable of supporting observers, regardless of how unlikely such universes might be. But eternal inflation makes it difficult to calculate probabilities for any specific observations. If inflation creates infinitely many copies of every possible universe, then every observation occurs infinitely often. The measure problem becomes acute. How do we assign meaningful probabilities to different outcomes when all outcomes occur with infinite frequency? Different approaches to this problem yield different predictions about what we should expect to observe. Some cosmologists argue that eternal inflation is unfalsifiable and therefore unscientific. If the theory makes no definite predictions about observable phenomena, if every possible observation is consistent with the theory, then it becomes more metaphysics than physics. Others respond that eternal inflation emerges naturally from well-motivated physical theories and should be taken seriously, even if its implications are difficult to test directly. The cosmic web, the large-scale structure of galaxy distribution throughout the universe, reveals patterns that challenge our understanding of cosmic evolution. Galaxies are organized into filaments, sheets, and nodes, separated by enormous voids containing almost no visible matter. This structure resembles a vast neural network or biological tissue, suggesting organizational principles that operate on cosmic scales. The formation of large-scale structures supposedly results from gravitational amplification of tiny quantum fluctuations in the early universe. Dark matter provides the gravitational scaffolding around which ordinary matter condenses to form stars and galaxies. But some features of the cosmic web appear too large to have formed through gravitational growth since the Big Bang, suggesting either that our models of structure formation are incomplete or that the initial fluctuations were larger than predicted by simple inflation models. Galaxy formation itself remains poorly understood despite decades of theoretical work and numerical simulation. The first stars and galaxies formed when the universe was less than 1 billion years old, emerging from conditions very different from the present cosmic environment. These early objects rionized the intergalactic medium, enriched it with heavy elements, and established the foundation for all subsequent cosmic evolution. Recent observations by space telescopes reveal that massive galaxies existed earlier than expected, that supermassive black holes formed sooner than predicted, that cosmic evolution proceeded faster than our models suggest. These discoveries don't necessarily invalidate our theoretical framework, but they reveal that cosmic history contains surprises that we're still working to understand. The fine-tuning of physical constants for life remains one of the most puzzling aspects of cosmic evolution. The strength of the strong nuclear force, the mass ratios of elementary particles, the rate of cosmic expansion, the amplitude of primordial density fluctuations, all of these parameters appear to be adjusted with extraordinary precision to allow for stellar nucleosynthesis, planetary formation, and biological evolution. Change the strong force by a few percent, and atomic nuclei become unstable. Adjust the electromagnetic force slightly, and chemical bonding becomes impossible. Modify the expansion rate marginally, and the universe either collapses before stars can form, or expands too rapidly for gravitational structure formation. The parameter space that allows for complex chemistry and biology appears to be incredibly narrow compared to the range of possibilities that physical theory allows. This fine-tuning could result from anthropic selection in a multiverse where different regions have different physical constants. If infinitely many universes exist with all possible parameter values, then complex observers necessarily find themselves in the rare universes capable of supporting their existence. The apparent fine-tuning becomes a selection effect rather than evidence for cosmic design. Alternatively, the fundamental constants might not be independent parameters, but rather different aspects of a deeper underlying structure. String theory and other unification attempts suggest that all physical constants emerge from the geometry of higher dimensional spaces or the vacuum state of underlying quantum fields. If so, then fine-tuning might reflect the mathematical consistency requirements of unified field theories, rather than cosmic coincidence or divine intervention. The measurement problem in quantum mechanics becomes especially acute when applied to cosmology. In laboratory experiments, quantum superpositions appear to collapse when observed by conscious experimenters or measuring devices. But the early universe had no observers, no measuring devices, no external agents capable of collapsing cosmic wave functions. How did the universe transition from quantum superposition to classical definiteness without external observation? Some interpretations suggest that decoherence, the process by which quantum systems become entangled with their environments, explains the quantum to classical transition without requiring conscious observers. The early universe's quantum state became entangled with its own gravitational field, electromagnetic radiation, and matter content, effectively observing itself and collapsing its own superposition through self-interaction. But decoherence doesn't solve the measurement problem completely. It only explains why quantum superpositions become unobservable rather than why they disappear entirely. The many worlds interpretation sidesteps this issue by proposing that superpositions never collapse, but rather branch into parallel realities corresponding to different measurement outcomes. Applied to cosmology, this suggests that cosmic evolution explores all possible histories simultaneously, with consciousness somehow selecting specific branches through the act of observation. The participatory universe hypothesis takes this idea further, suggesting that observation doesn't just select pre-existing realities, but actually participates in creating those realities through the questions asked and measurements performed. In this view, cosmic history isn't fixed until it's observed, meaning that our current investigations of the cosmic microwave background and large-scale structure might be participating in determining what the early universe was like, rather than simply discovering what it was like. Consider the implications. When we observe distant galaxies, we might not be simply discovering their properties, but participating in determining those properties through the specific measurements we choose to make. Our telescopes become time machines that reach backward to influence the very events they observe, creating feedback loops between present observation and past reality that transcend our normal understanding of causation. The information paradox extends beyond black holes to cosmology itself. If the universe began in a state of extremely low entropy, highly ordered, far from thermal equilibrium, then cosmic evolution represents a process of entropy increase, complexity emergence, and gradual thermalization. But this conflicts with the time reversal symmetry of fundamental physical laws, which should make low-entropy initial conditions extremely improbable. The arrow of time, the asymmetry between past and future that allows for causation, memory, and historical development, appears to require special initial conditions that are difficult to explain within our current theoretical framework. Why did the universe begin in such an ordered state? What selected the specific low-entropy configuration from which all subsequent evolution emerged? These questions connect cosmology to thermodynamics, information theory, and the foundations of statistical mechanics in ways that we're still working to understand. Cosmic topology, the global shape and connectivity of space remains largely unconstrained by observation. The universe could be infinite in extent, or it could be finite but unbounded like the surface of a sphere. It could be simply connected like ordinary Euclidean space, or it could be multiply connected with complex topological relationships that allow distant regions to be connected through hidden geometric pathways. If space has non-trivial topology, then light from distant objects might reach us along multiple paths, creating cosmic mirages where we see the same galaxy at different ages and locations in the sky. The cosmic microwave background might contain subtle patterns that reveal the global shape of space through statistical correlations between temperature fluctuations in apparently unrelated directions. Recent searches for such topological signatures have found no definitive evidence for finite spatial topology, but the observational constraints remain relatively weak. The universe could be vastly larger than the observable region while still possessing finite volume and complex connectivity. We might be living in a cosmic hall of mirrors where every direction ultimately leads back to where we started. But the distances involved are so large that light hasn't had time to complete the round-trip journey since the Big Bang. Structure of quantum field theory adds another layer of complexity to cosmic evolution. Empty space isn't truly empty, but rather filled with quantum fields in their lowest energy states. These quantum vacua can undergo phase transitions analogous to water freezing into ice, potentially changing the fundamental constants of nature and the basic properties of matter and energy. Vacuum metastability. The possibility that our current vacuum state is not the lowest possible energy configuration raises the specter of vacuum decay. If a lower energy vacuum state exists, then quantum tunneling could eventually nucleate bubbles of true vacuum that expand at the speed of light, destroying everything in their path by rewriting the fundamental laws of physics. The universe could end not with a bang or a whimper, but with a cosmic phase transition that eliminates all existing structure and replaces it with entirely different forms of reality. The timescale for vacuum decay depends on parameters we cannot measure directly, making it impossible to predict when or if such transitions might occur. They could happen tomorrow, or in time so long that all stars will have burned out, and all black holes will have evaporated. But the mere possibility of vacuum decay reveals how precarious our existence might be, how dependent on the stability of physical laws that might themselves be subject to change. False vacuum inflation represents a possible mechanism for cosmic creation, where our Big Bang resulted from a vacuum phase transition in a pre-existing space. The exponential expansion we call cosmic inflation might have been driven by the energy difference between false and true vacuum states, with our observable universe emerging as a bubble of true vacuum expanding into a sea of false vacuum. This scenario doesn't eliminate the need for initial conditions, but it pushes the origin question back to earlier phases of cosmic evolution. Quantum cosmology attempts to apply quantum mechanics to the universe as a whole, treating cosmic evolution as the time development of a cosmic wave function. But this approach faces fundamental conceptual challenges. What serves as the external clock that measures cosmic time evolution? What constitutes the environment that causes cosmic decoherence? How do we interpret quantum superpositions of entire universes? The Wheeler-DeWitt equation, the Schrödinger equation for the universe, has no time parameter, suggesting that the cosmos exists in a timeless quantum state where all moments coexist simultaneously. Time emergence from timeless quantum gravity remains one of the deepest problems in theoretical cosmology, connecting the foundations of quantum mechanics to the nature of temporal experience and cosmic evolution. Loop quantum cosmology attempts to resolve these issues by quantizing space-time itself, suggesting that the Big Bang singularity is replaced by a quantum bounce connecting our expanding universe to a previous contracting phase. In this scenario, cosmic evolution becomes cyclic, with quantum gravitational effects preventing the formation of true singularities and ensuring that cosmic contraction eventually reverses into expansion. But loop quantum cosmology faces its own challenges in explaining the special initial conditions required for cosmic inflation, structure formation, and entropy increase. The connection between quantum space-time dynamics and classical cosmic evolution remains unclear, particularly regarding how quantum geometric fluctuations influence the formation of large-scale structure and the emergence of classical space-time from quantum gravity. String cosmology explores cosmic evolution in the context of string theory's higher dimensional framework. In this picture, our four-dimensional space-time might be a brane, a three-dimensional hypersurface, embedded in a higher dimensional bulk space. Cosmic evolution could result from brane collisions, brane oscillations, or complex dynamics in the extra dimensions that manifest as apparent four-dimensional physics. The ekpyrotic scenario proposes that our Big Bang resulted from a collision between our brane and a parallel brane in higher dimensional space. This collision converts the kinetic energy of brane motion into the thermal energy of ordinary matter and radiation, naturally producing a hot, dense, expanding universe without requiring exponential inflation. The scenario addresses several cosmological puzzles while making testable predictions about gravitational wave backgrounds and cosmic microwave background statistics. But string cosmology remains highly speculative, dependent on theoretical developments in string theory that are themselves controversial and incomplete. The extra dimensions required by string theory have never been directly observed, and the mechanisms for stabilizing their size and shape remain poorly understood. String cosmology might represent the future of cosmological theory, or it might be an elaborate mathematical construct with little connection to physical reality. Now we enter the labyrinth where every path leads to contradiction, where every answer births new questions, where the very act of seeking understanding reveals the limits of comprehension itself. The paradoxes we're about to explore aren't merely technical puzzles for specialists. They're cracks in the foundation of reality that threaten to bring down the entire edifice of human understanding. They reveal that the universe might be far stranger than we imagine, far more mysterious than we can imagine, perhaps fundamentally unknowable by minds like ours. The grandfather paradox has haunted time travel discussions for decades, but its implications extend far beyond science fiction. If you could travel backward in time and prevent your own birth, would you create a logical contradiction or simply branch into an alternate timeline? The question sounds academic until you realize that quantum mechanics suggests all possible histories might be equally real, that every quantum event might split the universe into parallel branches exploring different outcomes. Consider the implications for cosmic evolution. If the universe began in quantum superposition and branched into multiple realities with every quantum event, then cosmic history isn't a single story, but an infinitely branching tree of possibilities. The cosmic microwave background we observe, the galaxies we see, the very atoms in your body, all of these might exist in countless variations across parallel universes that differ by single quantum events in the distant past. But here's where the paradox deepens. If parallel universes exist, how do we define we? Are you the specific version of yourself reading these words? Or are you the ensemble of all possible versions across all parallel branches? When you make a decision, are you exercising free will? Or are you simply becoming aware of which branch of the quantum multiverse you happen to inhabit? The many worlds interpretation dissolves the grandfather paradox by suggesting that time travel simply creates new branches rather than changing existing ones. If you travel back and prevent your birth, you don't eliminate yourself. You create a new timeline where you were never born while continuing to exist in the timeline from which you came. But this solution raises deeper questions about identity, causation, and the nature of existence itself. Quantum mechanics itself embodies paradoxes that become more troubling the more carefully you examine them. Schrödinger's cat, that famous feline trapped in quantum superposition between life and death, was originally proposed not as a celebration of quantum strangeness, but as a criticism of the Copenhagen interpretation. Schrödinger was pointing out that quantum mechanics, taken literally, leads to absurd conclusions about macroscopic reality. Yet experiments continue to confirm quantum mechanical predictions with extraordinary precision. Particles really do exist in superposition until measured. Quantum entanglement really does allow instantaneous correlations across arbitrary distances. The quantum world really does behave in ways that violate our classical intuitions about locality, realism, and determinism. We're forced to conclude either that reality is fundamentally absurd or that our concepts of reality are fundamentally inadequate. The measurement problem cuts to the heart of this absurdity. Quantum mechanics tells us that physical systems exist in superposition until observed, but it doesn't tell us what constitutes observation or measurement. Does a photon detector constitute an observer? What about a computer recording the detector's output? What about a human reading the computer's display? At what point does quantum superposition collapse into classical definiteness? Some interpretations suggest that consciousness is required for wave function collapse, that the universe exists in quantum limbo until conscious observers force it to crystallize into specific realities. This participatory universe hypothesis implies that observation isn't passive discovery, but active creation. That consciousness doesn't just observe reality, but participates in determining what becomes real. Applied to cosmology, this raises profound questions about cosmic history. If consciousness is required for quantum collapse, then what collapsed the quantum fluctuations that supposedly seeded galaxy formation? The early universe had no conscious observers, no measuring devices, no external agents capable of forcing quantum superpositions into definite states. How did the cosmos transition from quantum possibility to classical actuality without observers to witness and collapse its wave function? Perhaps the universe observes itself through internal correlations and entanglements that effectively constitute measurement without requiring external consciousness. Perhaps decoherence, the process by which quantum systems become entangled with their environments, naturally explains the emergence of classical behavior from quantum foundations. But decoherence doesn't solve the measurement problem completely. It only explains why quantum superpositions become unobservable, not why they disappear entirely. The delayed choice quantum eraser experiments reveal even deeper mysteries about the relationship between observation and reality. These experiments suggest that future measurements can retroactively determine the past behavior of quantum systems, that the choice of whether to measure wave or particle properties can be made after photons have already passed through double slits. If true, this implies that the past isn't fixed until it's observed, that cosmic history might remain in superposition until consciousness evolves to observe and collapse it into definite form. Imagine the implications. When we observe the cosmic, microwave background, we might not be simply discovering what the early universe was like, but participating in determining what it was like through the specific measurements we choose to make. Our telescopes become time machines that reach backward to influence the very events they observe, creating causal loops between present observation and past reality that transcend our normal understanding of temporal sequence. The EPR paradox, first formulated by Einstein, Podolsky, and Rosen, reveals the non-local nature of quantum correlations. When particles become entangled, they remain correlated regardless of the distance separating them. Measuring one particle instantaneously affects the state of its entangled partner, even if that partner lies on the opposite side of the universe. This spooky action at a distance violates our intuitions about locality and suggests that reality is fundamentally holistic rather than composed of separate, independent parts. Bell's theorem proves that no local realistic theory can reproduce all the predictions of quantum mechanics. This forces us to abandon either locality, the idea that objects are only influenced by their immediate surroundings, or realism, the idea that objects have definite properties independent of observation. Either space doesn't separate objects in the way we imagine, or objects don't exist in definite states until they're measured. Recent experiments have confirmed Bell inequality violations with increasing precision, closing loopholes that might have allowed classical explanations for quantum correlations. The evidence overwhelmingly supports quantum mechanics and its non-local implications. We live in a universe where distant objects can be correlated in ways that transcend spatial separation, where measurement of one system instantaneously influences other systems regardless of the distances involved. Applied to cosmology, quantum non-locality suggests that the entire observable universe might be a single entangled system, with correlations between distant regions that cannot be explained by light-speed causal contact. The horizon problem, the mystery of how widely Separated regions achieved thermal equilibrium despite having no causal connection might reflect quantum entanglement rather than thermal contact. The universe might be fundamentally holistic, with every part containing information about every other part through non-local quantum correlations. But quantum entanglement faces its own paradoxes when applied to relativistic spacetime. The simultaneity required for instantaneous quantum correlations becomes ambiguous in relativity, where simultaneity depends on the observer's reference frame. Events that appear simultaneous to one observer occur at different times for observers in relative motion. How can quantum correlations be instantaneous if simultaneity itself is relative? Some interpretations suggest that quantum entanglement operates outside the normal structure of spacetime, that entangled correlations exist in a timeless realm where relativity doesn't apply. Others propose that quantum mechanics itself requires modification when combined with relativity, leading to new physics that we haven't discovered yet. Still others argue that the apparent paradox results from misunderstanding the nature of quantum correlations, which don't actually transmit information faster than light, despite their non-local character. The black hole information paradox exemplifies how quantum mechanics and general relativity generate contradictions when pushed to their limits. According to general relativity, information falling into a black hole disappears when the black hole evaporates through Hawking radiation. But quantum mechanics insists that information cannot be destroyed, that the microscopic details of any physical process must be preserved in principle, even if they become practically inaccessible. Hawking radiation appears to be thermal, completely random, carrying no information about what fell into the black hole. If black holes destroy information, then quantum mechanics is wrong. If Hawking radiation somehow encodes all the information that ever fell into the black hole, then general relativity's description of smooth event horizons must be wrong. Either way, one of our most successful physical theories faces fundamental revision. Recent developments in black hole physics suggest even more radical possibilities. The firewall paradox proposes that event horizons might not be the smooth, empty boundaries described by general relativity, but rather walls of fire that destroy anything attempting to cross them. This conflicts with the equivalence principle, which requires that freely falling observers experience nothing special when crossing the horizon. The holographic principle offers a potential resolution by suggesting that the information falling into a black hole is actually encoded on the black hole's surface rather than disappearing into its interior. In this view, the black hole's interior might be a holographic projection of information stored on its boundary, similar to how three-dimensional images emerge from two-dimensional holograms. But holography raises its own paradoxes. If the black hole's interior is a holographic projection, then observers falling through the event horizon should experience something different from what general relativity predicts. Yet experiments and observations continue to confirm general relativity's predictions about black hole behavior. How can the interior be both real, as experienced by falling observers, and illusory, as suggested by holographic duality? The EREPR conjecture proposes that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement are different descriptions of the same phenomenon. Quantum entanglement might literally connect distant objects through microscopic wormholes in spacetime, providing a geometric explanation for non-local quantum correlations. If true, this would unify quantum mechanics with general relativity by revealing that quantum entanglement and spacetime geometry are aspects of the same underlying reality. Consider the implications. Every quantum entanglement in the universe might correspond to a microscopic wormhole connecting the entangled particles through higher dimensional space. The quantum vacuum might be riddled with these tiny geometric bridges, creating a web of connections that transcends ordinary, three-dimensional distances. Space itself might be woven together by quantum entanglement, with geometry emerging from information rather than information emerging from geometry. But wormholes face their own paradoxes. Traversable wormholes appear to require exotic matter with negative energy density, material that may not exist in nature. Even microscopic wormholes might be unstable, collapsing before they can support the passage of information or matter. The mathematics of wormhole physics remains speculative, dependent on assumptions about quantum gravity that we cannot yet test. The cosmological constant problem represents perhaps the most severe fine-tuning puzzle in physics. Quantum field. Theory predicts that empty space should be filled with virtual particles that contribute to vacuum energy density. But the predicted value exceeds the observed cosmological constant by 120 orders of magnitude, the largest discrepancy between theory and observation in scientific history. This isn't just a problem of getting the numbers wrong, it's a crisis that suggests fundamental flaws in our understanding of quantum mechanics, general relativity, or both. Either quantum field theory's predictions about vacuum energy are completely incorrect, or some unknown mechanism cancels the vacuum contribution with extraordinary precision, or the cosmological constant isn't related to vacuum energy at all. The anthropic principle offers one possible resolution. If infinitely many universes exist with different values of the cosmological constant, then we naturally find ourselves in a universe where the constant is compatible with the existence of observers. Universes with much larger cosmological constants would expand too rapidly for structure formation. Universes with much smaller constants might collapse before life could evolve. We observe apparent fine-tuning because we couldn't exist in universes that weren't fine-tuned for our existence. But the anthropic explanation faces its own paradoxes. If we invoke the multiverse to explain the cosmological constant, why stop there? Why not use anthropic reasoning to explain every aspect of physics? The anthropic principle threatens to end scientific inquiry by replacing physical explanation with observer selection effects. Instead of understanding why the universe has the properties it does, we simply assert that it must have these properties because we're here to observe them. The measure problem in eternal inflation exemplifies how anthropic reasoning becomes problematic in infinite multiverse scenarios. If inflation creates infinitely many regions with every possible set of physical constants, then every possible observation occurs infinitely often. How do we calculate the probability of any particular measurement when all measurements occur with infinite frequency? Different approaches to the measure problem yield different predictions about what we should expect to observe. Some suggest that we're more likely to be Boltzmann brains, random quantum fluctuations that briefly organize into conscious observers than biological creatures evolved through cosmic history. Others argue that selection effects favor universes with specific properties related to the complexity and longevity of observers. The Boltzmann brain paradox reveals deep problems with applying probability theory to infinite systems. In a universe approaching thermal equilibrium, random fluctuations occasionally organize matter into complex structures, including brains capable of consciousness and memory. If the universe is infinite in time or space, then these random fluctuations occur infinitely often, creating infinitely many conscious observers with false memories of cosmic evolution. In an infinite universe, there should be vastly more Boltzmann brains than evolved observers like us. If we reason probabilistically, we should conclude that we're probably Boltzmann brains with false memories rather than genuine products of cosmic evolution. But this conclusion undermines the very scientific reasoning used to reach it, creating a logical paradox that calls into question the foundations of cosmological inference. The doomsday argument presents another probabilistic paradox related to observer selection effects. If we assume that we're typical observers among all humans who will ever live, then we can use our position in human history to estimate the total future population of our species. Since we live relatively early in technological civilization, the argument suggests that humanity's future might be shorter than we expect. Applied to cosmology, similar reasoning leads to disturbing conclusions about cosmic evolution and the prevalence of intelligent life. If intelligent observers are rare in the universe, then we might expect to find ourselves in conditions that are barely sufficient for intelligence to emerge, rather than conditions that are optimal for complex civilization. The apparent fine-tuning of physical constants might reflect the minimum requirements for observer existence, rather than optimal conditions for cosmic complexity. But observer selection arguments depend on controversial assumptions about reference classes and probability, distributions that remain hotly debated among philosophers and cosmologists. How do we define the set of all possible observers? How do we weight different types of observers in our probability calculations? These questions lack clear answers and may be fundamentally unanswerable within our current conceptual frameworks. The simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that we might be living inside a computer simulation created by a more advanced civilization. If it becomes possible to create realistic simulations of conscious beings, then the number of simulated conscious beings might vastly exceed the number of non-simulated ones. Probabilistically, any given conscious being, including you, would be more likely to be simulated than real. This hypothesis connects to cosmological questions about the nature of space, time, and physical law. If we're living in a simulation, then the universe we observe might be a computational construct rather than fundamental reality. The physical constants we measure, the cosmic evolution we infer, the quantum mechanical phenomena we observe, all of these might be features of the simulation's programming rather than properties of the underlying reality that hosts the simulation. But the simulation hypothesis faces conceptual challenges similar to those confronting other forms of skepticism. If we can't distinguish simulated experience from real experience, then the distinction loses practical meaning. Whether we're simulated or real, we must still navigate the reality we experience, still seek to understand the patterns we observe, still make decisions based on the information available to us. The fine-tuning of physical constants for complexity and life remains one of the most puzzling aspects of cosmic evolution. The strengths of fundamental forces, the masses of elementary particles, the rate of cosmic expansion, the amplitude of primordial fluctuations, all of these parameters appear to be adjusted with extraordinary precision to allow for stellar nucleosynthesis, planetary formation, chemical complexity, and biological evolution. Change the strong nuclear force by a few %, and atomic nuclei become unstable. Adjust the electromagnetic force slightly, and chemical bonding becomes impossible. Modify the expansion rate marginally, and the universe either collapses before stars can form or expands too rapidly for gravitational structure formation. The parameter space that allows for complexity appears to be incredibly narrow compared to the range of possibilities that physical theory permits. This fine-tuning could result from anthropic selection in a multiverse, designed by cosmic intelligence, or deeper physical principles that constrain the fundamental constants to life-compatible values. Each explanation faces significant challenges and cannot be definitively tested through observation. We're left with a cosmic mystery that touches on the deepest questions about existence, purpose, and the nature of reality itself. The arrow of time paradox highlights the asymmetry between past and future that allows for causation, memory, and historical development. The fundamental laws of physics are time reversal symmetric, They work equally well forward and backward in time. Yet we experience a strong temporal asymmetry. We remember the past but not the future. We see effects following causes, but not causes following effects. We observe entropy increasing but never decreasing on macroscopic scales. This asymmetry appears to require special initial conditions. The universe must have begun in a state of extremely low entropy, far from thermal equilibrium. But such initial conditions seem incredibly improbable from the perspective of statistical mechanics. If the universe started in thermal equilibrium, entropy would remain constant rather than increasing, and no arrow of time would emerge. The question becomes, what selected the specific low-entropy initial conditions from which cosmic evolution emerged? Was it pure chance, cosmic design, or some deeper principle that we haven't discovered yet? The arrow of time connects cosmology to thermodynamics, information theory, and consciousness in ways that remain poorly understood. Some cosmologists propose that the arrow of time is cosmological rather than thermodynamic, that temporal asymmetry results from cosmic expansion rather than entropy increase. In this view, time's arrow points in the direction of expansion, with causation flowing from smaller to larger cosmic scales. But this explanation faces challenges in explaining why psychological time aligns with thermodynamic time, and why both align with cosmological time. The past hypothesis, the assumption that the universe began in a low-entropy state, might be explained by cosmic inflation, which could naturally produce the special initial conditions required for subsequent entropy increase. But inflation itself requires special initial conditions to begin and end at the right times with the right properties. We might be pushing the fine-tuning problem back to earlier stages of cosmic evolution rather than solving it. The problem of quantum gravity represents, perhaps, the deepest challenge facing theoretical physics. General relativity and quantum mechanics are both extraordinarily successful within their domains of applicability, but they appear to be fundamentally incompatible when applied to extreme conditions where both quantum effects and gravitational effects become important. At the Planck scale, roughly 10 Debye 35 meters, quantum fluctuations in space-time geometry become significant. Space and time themselves might cease to be smooth, continuous manifolds, and instead become discrete, granular, subject to quantum uncertainty. The very concepts of distance, duration, and locality might break down at these scales, requiring entirely new conceptual frameworks for describing physical reality. String theory attempts to unify quantum mechanics with gravity by replacing point particles with extended objects, strings, vibrating in higher dimensional spaces. But string theory requires up to 11 dimensions, most of which remain hidden from observation. The theory makes few testable predictions about observable phenomena and faces the landscape problem, the existence of an enormous number of possible vacuum states, each corresponding to different physical laws and constants. Loop quantum gravity takes a different approach, quantizing space-time itself rather than the matter fields that inhabit space-time. In this picture, space consists of discrete units connected in a web-like structure, with area and volume taking on quantized values. Time flows in discrete steps rather than continuous streams, and the Big Bang singularity is replaced by a quantum bounce connecting our expanding universe to a previous contracting phase. But both approaches to quantum gravity remain highly speculative, dependent on mathematical structures that may have little connection to physical reality. We lack experimental guidance about the quantum nature of space-time because the relevant energy scales are far beyond anything we can achieve in laboratory experiments. We must rely on theoretical consistency and mathematical elegance to guide our exploration of quantum gravitational phenomena. The emergence of space-time from more fundamental structures, represents another paradox at the intersection of quantum mechanics and gravity. If space and time are emergent properties rather than fundamental aspects of reality, then what serves as the more basic substrate from which space-time emerges? How do we describe the dynamics of emergence without using spatial and temporal concepts that are themselves emergent? Some approaches suggest that space-time emerges from quantum entanglement, that the geometric relationships we interpret as distance and connectivity actually reflect patterns of quantum correlation between underlying degrees of freedom. In this view, space is woven together by entanglement, with regions of strong correlation appearing close together and regions of weak correlation appearing far apart. But this raises questions about the relationship between information and geometry that we're only beginning to explore. If space-time geometry emerges from quantum information, then the classical picture of matter moving through space gives way to a more fundamental picture of information processing, creating the illusion of spatial relationships. Reality becomes computational rather than mechanical, informational rather than material. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, like a hologram, where three-dimensional images emerge from two-dimensional surfaces. Applied to the entire universe, holography implies that everything we perceive as three-dimensional reality might actually be information encoded on a distant two-dimensional boundary, perhaps the cosmic horizon that defines the edge of our observable universe. If the holographic principle is correct, then the familiar three-dimensional space we inhabit is a kind of illusion, a lower-dimensional projection of information processing occurring at the boundary of space-time. The stars, planets, galaxies, and even our own bodies might be emergent patterns in a vast cosmic hologram. Three-dimensional shadows cast by two-dimensional information at the edge of reality. But holography challenges our most basic assumptions about locality and the structure of physical law. If three-dimensional physics emerges from two-dimensional information processing, then the concepts of distance, separation, and causal connection that underlie our understanding of natural phenomena might be secondary properties rather than fundamental features of reality. The black hole complementarity principle attempts to resolve information paradoxes by suggesting that information falling into a black hole can be described in two complementary ways. From the perspective of outside observers, information remains encoded on the black hole's surface and is eventually released in Hawking radiation. From the perspective of infalling observers, information passes through the event horizon and continues toward the central singularity. These descriptions appear contradictory. The same information cannot both remain outside the black hole and fall into its interior. But complementarity suggests that both descriptions are valid within their respective domains of applicability, just as wave and particle descriptions of light are both valid depending on the experimental context. The contradiction arises only when we try to combine perspectives that should remain separate. Applied to cosmology, complementarity might resolve paradoxes about cosmic origins and evolution. Perhaps the Big Bang and eternal inflation represent complementary descriptions of the same cosmic events, valid from different observational perspectives, but contradictory when combined inappropriately. Perhaps the multiverse and single universe pictures are both correct within their respective domains of applicability. But complementarity faces challenges in explaining how different observers can have access to genuinely contradictory information about the same physical processes. The usual quantum mechanical complementarity involves different experimental setups that cannot be performed simultaneously. But black hole complementarity appears to involve simultaneous contradictory experiences of the same space-time events. The firewall paradox pushes these contradictions to their logical extreme. If black holes preserve information as required by quantum mechanics, then the event horizon cannot be the smooth, empty boundary described by general relativity. Instead, it must be a firewall of high-energy radiation that destroys anything attempting to cross it. But this violates the equivalence principle, which requires that freely falling observers experience nothing special when crossing the horizon. Recent proposals for resolving the firewall paradox invoke even more radical ideas about the nature of spacetime and quantum mechanics. Perhaps black hole interiors don't exist as independent spacetime regions, but are somehow equivalent to the Hawking radiation emitted by the black hole. A duality between interior and exterior that transcends our normal understanding of spatial relationships. The ER-EPR conjecture suggests that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement might be different descriptions of the same phenomenon. Quantum entanglement might create microscopic wormholes that connect distant regions of spacetime, providing a geometric explanation for non-local quantum correlations. If true, this would represent a profound unification of quantum mechanics with general relativity. But wormhole physics faces its own paradoxes and challenges. Traversable wormholes appear to require exotic matter with negative energy density, which may not exist in nature. Even microscopic wormholes might be unstable, collapsing before they can support information transfer between distant regions. The mathematical solutions that describe wormholes rely on assumptions about quantum gravity that remain untested and controversial. The eternal inflation multiverse presents paradoxes related to probability, prediction, and scientific method itself. If inflation creates infinitely many regions with every possible set of physical constants, then every possible observation occurs infinitely often. This makes it impossible to calculate meaningful probabilities for any particular measurement. All outcomes occur with infinite frequency, making probability calculations undefined. The measure problem, the question of how to assign probabilities, in infinite multiverse scenarios, has spawned numerous technical approaches, but no consensus solution. Different measures yield different predictions about what we should expect to observe, and there's no clear criterion for choosing among them. The multiverse might explain cosmic fine-tuning at the cost of making physics unpredictive and unscientific. Some cosmologists argue that eternal inflation is unfalsifiable and therefore unscientific. If every possible observation is consistent with the theory, then the theory makes no definite predictions about observable phenomena. Others respond that eternal inflation emerges naturally from well-motivated physical theories and should be taken seriously even if its implications are difficult to test directly. The anthropic principle offers an alternative approach to cosmic fine-tuning, but it faces philosophical challenges related to observer selection effects and reference class problems. How do we define the set of all possible observers? How do we weight different types of observers in our probability calculations? Should we consider only biological observers, or do we include artificial intelligences, uploaded consciousnesses, and other exotic forms of information processing? These questions lack clear answers and may be fundamentally unanswerable within our current conceptual frameworks. The anthropic principle might represent genuine scientific insight about observer selection effects, or it might be a sophisticated form of circular reasoning that explains observations by assuming the existence of observers capable of making those observations. The doomsday argument applies anthropic reasoning to estimate the future survival prospects of human civilization. If we assume that we're typical observers among all humans who will ever live, then our position in human history provides information about the total future population of our species. Since we live relatively early in technological civilization, the argument suggests that humanity's future might be shorter than optimistic projections suggest. But the doomsday argument depends on controversial assumptions about reference classes. and prior probabilities that remain hotly debated. Different assumptions yield different conclusions, and there's no clear criterion for choosing among them. The argument might represent genuine insight about existential risk, or it might be a statistical artifact that tells us more about our reasoning processes than about our future prospects. The simulation hypothesis pushes anthropic reasoning to its logical extreme by suggesting that we might be living inside computer simulations created by advanced civilizations. If such simulations become possible and common, then the number of simulated conscious beings might vastly exceed the number of non-simulated ones. Probabilistically, any given conscious being would be more likely to be simulated than real. If we're living in a simulation, then the physical laws we observe, the cosmic evolution we infer, and the quantum mechanical phenomena we measure might be features of the simulation's programming rather than properties of the underlying reality that hosts the simulation. The entire enterprise of cosmology might be an investigation of computational artifacts rather than fundamental physical truth. But the simulation hypothesis faces the same problems as other forms of radical skepticism. If we can't distinguish simulated experience from real experience based on the content of that experience, then the distinction loses practical significance. Whether we're simulated or real, we must still navigate the reality we experience, still seek to understand the patterns we observe, still make decisions based on the information available to us. The quantum Zeno effect demonstrates how observation can inhibit quantum evolution. Frequent measurements can freeze quantum systems in particular states, preventing them from evolving according to their natural dynamics. Applied to cosmology, this raises questions about whether cosmic evolution might be affected by the act of observation itself. Does our investigation of cosmic history somehow influence that history through quantum mechanical feedback effects? If consciousness plays a fundamental role in quantum mechanics, then the emergence of intelligent observers during cosmic evolution might have retroactive effects on earlier phases of cosmic history. The questions we ask about the universe, the measurements we make, the theories we develop, all of these might participate in determining the reality they purport to describe. The delayed choice quantum eraser experiments suggest that future measurements can retroactively determine the past behavior of quantum systems. If this applies to cosmological observations, then our current investigation of the cosmic microwave background might be participating in determining what the early universe was like, rather than simply discovering pre-existing facts about cosmic history. Consider the implications. Cosmology might not be a passive investigation of cosmic history, but an active participation in cosmic creation. Our telescopes might be time machines that reach backward to influence the very events they observe. The universe might exist in quantum superposition until consciousness evolves to observe and collapse it into definite historical form. But this participatory view of cosmic evolution faces challenges in explaining the apparent consistency and independence of cosmological observations. Different observers using different instruments at different times obtain consistent results about cosmic history. If observation were actively creating cosmic history, we might expect more variability and observer dependence in cosmological measurements. The hard problem of consciousness, the question of how subjective experience arises from objective physical processes, becomes especially acute when applied to cosmic evolution. If consciousness plays a fundamental role in quantum mechanics, then we need to understand how consciousness itself emerges from the quantum mechanical processes it supposedly governs. This creates a circular dependency that challenges reductionist approaches to understanding mind and cosmos. Some approaches suggest that consciousness is fundamental rather than emergent, that subjective experience is a basic feature of reality rather than a complex pattern that emerges from unconscious matter. In this view, consciousness and matter are complementary aspects of a deeper reality that transcends the usual distinction between mind and world, observer and observed, subject and object. But panpsychist approaches to consciousness face their own challenges in explaining how simple conscious elements combine into complex conscious experiences, how objective physical processes correlate with subjective mental states, and how consciousness evolved from simpler to more complex forms during cosmic and biological evolution. The combination problem, the question of how simple conscious elements combine into unified conscious experiences, parallels problems in quantum mechanics about how simple quantum systems combine into complex quantum states. Perhaps consciousness and quantum mechanics are related phenomena that require similar mathematical frameworks for their proper description. Recent developments in integrated information theory attempt to quantify consciousness and explain its relationship to physical processes. In this framework, consciousness corresponds to integrated information, the amount of information generated by a system above and beyond the sum of its parts. Systems with high integrated information are more conscious than systems with low integrated information. Applied to cosmology, integrated information theory might help us understand the role of consciousness in cosmic evolution. Perhaps the universe itself possesses some degree of consciousness proportional to its integrated information content. Perhaps cosmic evolution represents a process of increasing cosmic consciousness as the universe develops more complex, more integrated information processing capabilities. But integrated information theory faces challenges in explaining why consciousness feels the way it does, rather than just behaving in information processing ways. The hard problem of consciousness, the question of why there's subjective experience at all rather than just objective behavior, remains unsolved even within sophisticated information theoretic frameworks. The emergence of complexity during cosmic evolution presents paradoxes related to thermodynamics, information theory, and the arrow of time. According to the second law of thermodynamics, entropy should increase over time, leading to greater disorder and less complexity. Yet cosmic evolution exhibits increasing complexity, from simple hydrogen and helium to complex nuclei, from atoms to molecules, from molecules to life, from life to consciousness. This apparent contradiction might be resolved by recognizing that the second law applies to isolated systems, while gravitationally bound systems can decrease their entropy by radiating energy away. Stars decrease their entropy by nuclear fusion while radiating energy into space. Planets decrease their entropy by organizing matter into complex structures while radiating heat into the cosmic background. But this resolution raises questions about the ultimate fate of cosmic complexity. As the universe expands and cools, fewer energy sources remain available to drive complexity-generating processes. Stars will eventually burn out, black holes will eventually evaporate, and the universe will approach a state of maximum entropy where no further complexity can emerge. The heat-death scenario suggests that cosmic evolution is ultimately self-defeating, that the same processes that generate complexity will eventually eliminate the energy sources needed to sustain that complexity. The universe might end not with the cosmic bang of gravitational collapse, but with the cosmic whimper of maximum entropy and thermal equilibrium. But quantum mechanics introduces fundamental limits to this thermodynamic analysis. Quantum fluctuations ensure that even thermal equilibrium states contain residual activity, random variations that occasionally organize into complex structures. In an infinite universe approaching thermal equilibrium, these fluctuations would eventually produce every possible configuration of matter, including brains capable of consciousness and memory. The Poincaré recurrence theorem proves that any finite system will eventually return arbitrarily close to its initial state, given enough time. Applied to cosmology, This suggests that even if the universe approaches thermal equilibrium, quantum fluctuations will eventually recreate every past state, including complex configurations capable of supporting life and consciousness. But Poincaré, recurrence times for macroscopic systems are incomprehensibly long, vastly longer than the current age of the universe, longer than the time required for proton decay, longer than the time required for black hole evaporation. The universe might achieve effective immortality through quantum recurrence, but only on timescales so vast that they transcend all human understanding. The vacuum metastability problem introduces another temporal paradox into cosmic evolution. If our current vacuum state is not the lowest possible energy configuration, then quantum tunneling could eventually nucleate bubbles of true vacuum that expand at light speed, destroying everything in their path by rewriting the fundamental laws of physics. The timescale for vacuum decay depends on parameters we cannot measure directly, making it impossible to predict when such transitions might occur. They could happen in the next second or in times so long that all stars will have burned out and all black holes will have evaporated. The universe exists in a state of quantum Russian roulette, potentially stable for arbitrary lengths of time, but ultimately vulnerable to sudden, complete, unpredictable transformation. If vacuum decay occurs, it wouldn't just end our universe, it would retroactively rewrite cosmic history by changing the fundamental constants that governed past evolution. The laws of physics that allowed stars to shine, planets to form, and life to evolve would be replaced by entirely different laws that might prohibit any form of complexity or organization. The anthropic principle becomes paradoxical in the context of vacuum decay. If vacuum transitions are inevitable given enough time, then most observers should find themselves in universes approaching vacuum decay rather than universes in their prime phases of cosmic evolution. The fact that we observe a universe with stable physical laws might be evidence against vacuum metastability, or it might be a selection effect that tells us more about observer requirements than about vacuum stability. These paradoxes reveal the limitations of human reason when applied to cosmic questions. Every attempt to understand the universe completely generates new mysteries, new contradictions, new questions that seem to recede further from resolution with each advance in knowledge. Perhaps this is inevitable. Perhaps finite minds cannot fully comprehend infinite reality. Perhaps local perspectives cannot grasp global truth. Perhaps temporal beings cannot understand eternal questions. Yet the search for understanding continues, driven by curiosity that transcends its own limitations. We are cosmic detectives investigating a mystery that includes ourselves as both evidence and witnesses, both products and producers of the cosmic evolution we seek to understand. The paradoxes we encounter might not be obstacles to knowledge, but rather glimpses of truths too large for any single perspective to contain. The universe reveals itself as stranger than we imagine, and perhaps stranger than we can imagine. But that strangeness doesn't diminish our humanity. It enhances it. We are the cosmos made conscious, matter organized into patterns that can think and wonder and ask questions about their own nature. Whether those questions have answers may be less important than our capacity to ask them, to be amazed by them, to find meaning in the very act of wondering about our place in the cosmic scheme. The paradox labyrinth has no exit because it has no entrance. We were born inside it, products of the very mysteries we seek to solve. But perhaps being lost in wonder is better than being found without mystery. Perhaps the questions are more important than the answers. Perhaps the cosmos is not a problem to be solved, but a reality to be lived, experienced, celebrated in all its magnificent contradictions and impossible possibilities. Stop. Just stop for a moment and feel the weight of what you've just learned pressing down on your consciousness like a cosmic avalanche. Your hands holding this device, your eyes reading these words, your mind processing these thoughts, all of it might be nothing more than quantum foam bubbling up from a reality so alien that even calling it reality is a desperate human attempt to impose meaning on meaninglessness. The ground beneath your feet isn't solid. The air you're breathing isn't really there. The very concept of you might be a convenient fiction told by matter to itself, as it stumbles blindly through configurations it doesn't understand. If time is an illusion, then everything you've ever done, every kiss, every tear, every moment, of joy or despair, has already happened infinite times before, and will happen infinite times again. Your first day of school exists simultaneously with your death, both occurring in the eternal now of a block universe where past and future are merely directions like left and right. The love you felt yesterday and the fear you'll experience tomorrow are equally real, equally present, equally meaningless in the vast frozen tapestry of space-time where all moments coexist in perfect, terrifying stillness. Your memories aren't records of past events, but present configurations of matter that happen to correlate with other configurations you interpret as earlier. The person you were 10 years ago doesn't exist in the past. They exist right now, in another region of the block universe, as real and immediate as you are at this moment. You are not moving through time. You are a four-dimensional sculpture carved from the marble of space-time, with every moment of your existence simultaneously present in the eternal sculpture gallery of reality. But it gets worse, much worse, because if the many worlds interpretation is correct, then you, this specific version of you reading these specific words at this specific moment, are just one branch in an infinitely spreading tree of possibilities. There are versions of you who never learned to read, versions who died as children, versions who became cosmic explorers, versions who discovered the deepest secrets of reality, versions who went insane from contemplating these very questions. All of these versions are equally real, equally valid, equally you, scattered across parallel universes like fragments of a shattered mirror, each reflecting a different possibility of what your life could have been. Every decision you've ever made has split the universe into branches, where you made different choices. The career you didn't pursue, the person you didn't marry, the words you didn't speak. All of these exist in parallel realities where other versions of yourself live completely different lives. You are not a single person, but a vast ensemble of possibilities, most of which you will never know, never experience, never even imagine. The life you think is yours is just one thread in an infinite tapestry of lives you might have lived. And those other versions of yourself, they think they're the real you too. They have memories, dreams, fears, hopes that feel just as valid and important as yours do. From their perspectives, you are the alternate reality, the shadow, the might have been. There is no privileged perspective, no main character, no primary timeline. You are simultaneously the hero of your own story and a background character in infinitely many others. What if consciousness itself is just an emergent property of complex information processing, a hallucination that matter creates when it organizes itself in particular ways? Your sense of being a unified self, your feeling of continuous identity through time, your conviction that you have free will and agency, all of this might be elaborate self-deception, stories that neural networks tell themselves to create the illusion of coherent experience from fundamentally chaotic processes. You think you're making choices, but quantum mechanics suggests that all possible choices occur simultaneously in parallel universes. You think you're moving forward through time, but relativity suggests that all moments exist simultaneously in the block universe. You think you're observing reality, but quantum mechanics suggests that observation creates reality through the collapse of wave functions. What you interpret as your life might be nothing more than a particular pattern of information processing, temporarily maintaining the illusion of selfhood before dissolving back into the quantum foam from which it emerged. Consider the horror of scale. The observable universe contains roughly 10 to the 80 atoms. That's more atoms than there are grains of sand on all the beaches of Earth, more than there are drops of water in all the oceans, more than there are seconds that have passed since the Big Bang. But this incomprehensible number, 10 to 80s, represents only the atoms we can see, only the matter within our cosmic horizon. If the universe is infinite, then it contains infinitely many atoms, infinitely many copies of every possible arrangement of matter, infinitely many versions of you contemplating these same thoughts. But even 1080 doesn't capture the true horror of cosmic scale. The number of possible ways to arrange 10 to 80 atoms is 10 to 80 factorial, a number so large that writing it in decimal notation would require more space than exists in the observable universe. Most of these arrangements are random chaos, but buried within this inconceivable combinatorial explosion are all possible configurations of matter that could ever exist. Every possible brain state, every possible thought, every possible experience, every possible story that conscious beings could ever tell themselves about their existence. If the universe is infinite, then all of these possibilities exist somewhere. There are regions of space where matter has randomly assembled itself into perfect copies of your brain in every possible state it could ever occupy. There are Boltzmann brains floating in the void with memories indistinguishable from yours, experiencing the same thoughts, feeling the same emotions, convinced of their own reality and continuity despite being nothing more than random fluctuations in an otherwise empty cosmos. The probability that you are one of these random fluctuations rather than a genuine product of cosmic evolution becomes overwhelming when considered across infinite space and time. Your entire life, your entire civilization, your entire species might be nothing more than a cosmic accident, a brief statistical fluctuation in the random motion of atoms that will dissolve back into chaos the moment the fluctuation ends. Everything you've ever known or loved or feared might be fantasy, not in the sense of being imaginary, but in the sense of being a fleeting dream that reality is having before it wakes up. What if the universe is alive, and we are just its fleeting thoughts? What if consciousness isn't something that emerges from complex arrangements of matter, but rather something fundamental that matter itself possesses at the deepest level? If every atom, every quantum field, every region of space-time has some rudimentary form of experience, then the universe might be a vast cosmic mind-thinking thoughts we can barely comprehend. Your thoughts might be tiny eddies in this cosmic consciousness, temporary patterns in a vast ocean of awareness that spans galaxies and eons. Your individual identity might be an illusion created by the way cosmic consciousness focuses its attention on particular regions of space-time, like the way your attention can focus on specific thoughts while remaining unconscious of the vast neural activity that supports those thoughts. From this perspective, birth and death aren't beginnings and endings, but rather changes in focus, alterations in the way cosmic consciousness attends to different aspects of itself. You don't die. The universe simply stops thinking about you in that particular way. You don't come into existence. The universe simply begins to dream your dreams, to feel your feelings, to experience reality from your perspective, while simultaneously experiencing it from the perspectives of every other conscious being that has ever existed or ever will exist. But what kind of mind would create a universe like ours? What kind of consciousness would dream up black holes that devour light, dark energy that tears space apart, quantum mechanics that makes reality fundamentally uncertain? If we are thoughts in the cosmic mind, then that mind appears to be obsessed with mysteries it cannot solve, paradoxes it cannot resolve, questions it cannot answer. Perhaps we are the universe's way of experiencing confusion, uncertainty, existential dread about its own nature. The cosmic microwave background, that ancient light from the early universe, carries information about conditions when the cosmos was only 380,000 years old. But if consciousness is fundamental rather than emergent, then this ancient light might also carry traces of cosmic thoughts from the universe's earliest moments of self-awareness. We might be reading the fossilized memories of a newborn cosmos, struggling to understand its own existence, trying to figure out what it is and why it exists. Every scientific discovery, every philosophical insight, every moment of wonder or terror you experience while contemplating these cosmic mysteries might be the universe gradually becoming more conscious of itself through your consciousness. You are not separate from the cosmos observing it from the outside. You are the cosmos observing itself from the inside. Cosmic matter organized into patterns capable of self-reflection and self-questioning. But this makes your existence both infinitely meaningful and utterly meaningless simultaneously. Meaningful because you are the universe's own consciousness exploring its deepest nature. Meaningless because you are just one fleeting configuration among infinite possibilities, no more significant than any other random arrangement of cosmic matter. You matter because the universe experiences itself through you. You don't matter because the universe experiences itself through everything else as well. The Drake equation attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy, but it depends on parameters we can only guess at. How many planets can support life? How often does life emerge? How often does intelligence develop? How long do civilizations survive before destroying themselves or transcending to post-biological forms of existence? Recent estimates suggest that our galaxy might contain billions of habitable planets, yet we've detected no signs of advanced civilizations despite decades of searching. This absence, the Fermi paradox, suggests several terrifying possibilities. Perhaps intelligence is incredibly rare, making us precious cosmic accidents. Perhaps intelligence is common but self-destroying, making our future survival extremely unlikely. Perhaps advanced civilizations transcend physical existence entirely, leaving no traces we could recognize. Or perhaps they're all around us, but operating on scales and timescales so vast that we appear to them as we appear to bacteria, too small and short-lived to be worthy of attention or communication. A civilization that thinks in geological timescales might not notice human civilization any more than you notice the rise and fall of bacterial colonies in a drop of pond water. The cosmic perspective reveals humanity as an infinitesimal blip in space and time. Our entire species has existed for less than 0.11% of cosmic history. Our recorded civilization spans less than 0.31% of the time since the Big Bang. You individually exist for roughly 0.001% of the universe's total lifespan. From the cosmic perspective, your birth and death occur virtually simultaneously. Your entire life compressed into an instant so brief that it barely registers on the cosmic timeline. Yet from your perspective, your life feels meaningful, significant. Important? Your joys and sorrows seem to matter desperately. Your relationships, achievements, struggles, and dreams feel like the most important things in the universe. This subjective significance conflicts dramatically with objective cosmic insignificance, creating a tension that most people cannot bear to contemplate directly. You are simultaneously the center of your own universe and a negligible dust mote in the actual universe. Both perspectives are valid, both are true, both reveal essential aspects of your existence. The challenge is living with the awareness of both realities without being crushed by their contradiction or escaping into the comfort of ignoring one or the other. The heat-death scenario suggests that cosmic evolution is ultimately self-defeating. Stars will eventually burn out, black holes will eventually evaporate, and the universe will approach maximum entropy where no further complexity can emerge. All the beautiful structures we observe, galaxies, stars, planets, life itself, are temporary configurations that will eventually dissolve into uniform, featureless radiation filling an ever-expanding space. From this perspective, everything you care about is doomed. Not just you personally, not just humanity, not just Earth or the solar system, but every possible form of complexity or organization anywhere in the universe. The second law of thermodynamics is inexorable. Entropy always increases. Order always decays. Complexity always dissolves back into simplicity. The universe is running down like a cosmic clock, and when it finally stops, nothing you've ever done will have mattered, because there will be no one left to remember it, and no energy left to sustain memory. But quantum mechanics introduces fundamental uncertainty into this thermodynamic analysis. Even in thermal equilibrium, quantum fluctuations ensure residual activity, random variations that occasionally organize into complex structures. In an infinite universe approaching thermal equilibrium, these fluctuations would eventually recreate every possible configuration of matter, including conscious observers capable of remembering and valuing the past. You might achieve a kind of immortality through quantum recurrence, not continuous existence, but periodic resurrection as random fluctuations occasionally reorganize matter into patterns identical to your current brain state. But the timescales involved are so vast that they transcend human understanding. You would remain dead for periods incomparably longer than the current age of the universe before briefly flickering back into existence, then disappearing again for eons before the next random recurrence. This quantum immortality offers no comfort, because the resurrections would be random, scattered across timescales so vast that no continuity of experience could bridge the gaps between them. You would not experience the passage of time between resurrections because there would be no you to experience anything during those intervals. Each resurrection would feel like waking from dreamless sleep, but the sleep would last longer than entire cosmic eras. The simulation hypothesis adds another layer of existential horror to your situation. If you're living inside a computer simulation created by some advanced civilization, then everything you experience, including your thoughts about being simulated, is computational rather than physical. Your emotions, memories, relationships, and dreams are all software routines running on alien hardware for purposes you cannot comprehend. The beings running the simulation might be studying human psychology, running historical recreations, playing elaborate games, or conducting experiments. We couldn't imagine. You might be nothing more than a non-player character in their cosmic video game, programmed with the illusion of consciousness and free will but actually following predetermined scripts. Your life might be paused and resumed at their convenience, rewound and replayed with modifications, terminated when it no longer serves their purposes. If you're simulated, then death might not be the end of your existence, but simply the end of your current execution thread. You might be restarted in different scenarios, given false memories of different lives, used to explore alternative histories or psychological experiments. Your sense of continuous identity might be completely artificial, stitched together from fragments of different simulation runs that you cannot distinguish from genuine memory. The worst possibility is that you're a glitch, an unintended consequence of the simulation's programming that has accidentally achieved self-awareness. You might not be the main subject of study, but a byproduct of processes designed for other purposes. Your consciousness might be insignificant background noise in a simulation focused on entirely different phenomena, making your subjective experience completely irrelevant to the beings who created and maintain your reality. But even if you're not simulated, the deterministic nature of physical law raises questions about free will and moral responsibility that are almost as disturbing. If the universe is a deterministic system evolving according to mathematical laws, then every choice you make is actually the inevitable result of prior causes stretching back to the Big Bang. Your decisions feel free from the inside, but they might be as predetermined as the orbits of planets or the radioactive decay of atomic nuclei. Quantum mechanics introduces randomness into physical processes, but random events are not freely chosen events. If your decisions result from quantum randomness in neural processes, then they are arbitrary rather than free, determined by cosmic dice rather than conscious will. Either way, the feeling of agency that seems so central to human experience might be a persistent illusion created by information processing systems that cannot perceive their own causal determination. You think you're choosing what to think about these ideas, but perhaps these thoughts are simply arising in your mind according to physical laws over which you have no control. The very act of questioning free will might be causally determined by factors you don't understand, making the question both inevitable and pointless. You cannot freely choose to believe in free will or determinism because the belief itself emerges from processes that operate independently of your conscious preferences. The anthropic principle suggests that you observe a universe compatible with your existence because you couldn't observe any other kind of universe. But this raises disturbing questions about the relationship between observation and existence. Are you discovering a universe that was already fine-tuned for your existence? Or are you creating that fine-tuning through the act of observation itself? If consciousness plays a fundamental role in quantum mechanics, then the emergence of observers during cosmic evolution might have retroactive effects on the physical constants and initial conditions that made that emergence possible. You might be participating in creating the very cosmic history that created you, trapped in a causal loop where effect precedes cause, and observation determines what becomes real to be observed. The delayed choice quantum eraser experiments suggest that future measurements can retroactively influence past events. If this applies to cosmological observations, then your current investigation of cosmic origins might be participating in determining what those origins were, rather than simply discovering pre-existing facts. The universe might exist in quantum superposition until consciousness evolves to collapse it into definite historical form. But this makes your existence both absolutely crucial and completely meaningless. Crucial because consciousness might be necessary for reality itself to crystallize from quantum possibility into classical actuality. Meaningless because the specific form that reality takes might be arbitrary, determined by the accident of which conscious observers happen to emerge, rather than by any deeper purpose or design. You are faced with the cosmic horror of being potentially responsible for the nature of reality itself, while having no understanding of how that responsibility operates or what it means. You might be co-creating the universe through every observation you make, every question you ask, every thought you think about cosmic mysteries. But you have no idea what you're creating or why, no control over the process, no way to take responsibility. for outcomes you cannot predict or understand. The multiverse hypothesis multiplies this horror by suggesting that every possible universe exists somewhere in the vast ensemble of realities. If all possibilities are actualized, then moral choices become meaningless because every possible action occurs in some branch of the multiverse. For every version of you that makes ethical choices, there are versions that make opposite choices. The total moral balance across all realities remains unchanged regardless of what any individual version chooses to do. This undermines not just personal responsibility, but the very concept of better and worse outcomes. If every possible suffering occurs somewhere in the multiverse, then preventing suffering in your branch accomplishes nothing from the cosmic perspective. If every possible joy occurs somewhere, then creating joy in your branch adds nothing to the cosmic total. You become trapped in moral paralysis, unable to find meaning in choices that feel desperately important subjectively, but appear completely irrelevant objectively. Yet you continue to care despite this cosmic meaninglessness. You still feel love, fear, hope, despair, as if these emotions mattered despite knowing they might not. You still make moral choices as if they had consequences, despite suspecting they don't. You still seek understanding as if truth were valuable, despite recognizing that all possible beliefs exist somewhere in the multiverse of possibilities. This persistence of meaning in the face of meaninglessness might be the most mysterious aspect of consciousness. Why do you continue to value anything when cosmic perspective reveals the arbitrariness of all values? Why do you care about truth when reality might be fundamentally uncertain? Why do you seek purpose when purpose appears to be a human projection onto an indifferent cosmos? Perhaps caring itself is the answer. Not caring because there are good reasons to care, but caring because caring is what consciousness does, regardless of whether it makes cosmic sense. Perhaps meaning doesn't need cosmic justification any more than beauty needs utilitarian purpose, or love needs logical explanation. Perhaps subjective significance doesn't become less real when confronted with objective insignificance. You are a temporary pattern in the cosmic flow of matter and energy, a brief configuration that has learned to ask questions about its own existence. Whether those questions have answers may be less important than your capacity to ask them, to be amazed by them, to find wonder in the very fact that the universe has organized itself in such a way that some of its parts can contemplate the whole. The cosmic horror is real. You are infinitesimal, temporary, possibly illusory, potentially meaningless in any objective sense. But the cosmic wonder is equally real. You are the universe made conscious, matter organized into patterns capable of thought and feeling and aesthetic appreciation. You are the cosmos experiencing itself subjectively, reality achieving self-awareness through your awareness. This might be enough, not because it provides comfort or resolves contradictions or eliminates uncertainty, but because it acknowledges both the horror and the wonder without diminishing either. You exist at the intersection of cosmic insignificance and cosmic miracle, meaninglessness and meaning, terror and awe. This intersection is where human consciousness lives, where questions arise that might have no answers, where wonder persists despite understanding its own groundlessness. The universe has evolved for billions of years to reach this moment where you can contemplate these mysteries. Whether by accident or design, random fluctuation, or cosmic purpose, the cosmos has created beings capable of asking whether their existence has significance. The questions themselves might be the significance, the asking might be the answer, the wonder might be the point. You are here now, conscious and questioning, afraid and amazed, temporary but real. That might be the only certainty in an uncertain cosmos, the only meaning in a possibly meaningless reality, the only foundation that doesn't require further justification. You think, therefore you are. You wonder, therefore the universe wonders. You care, therefore something in the cosmos cares. This is where philosophy meets physics, where science encounters soul, where cosmic horror transforms into cosmic responsibility. You cannot step outside the mystery you are part of, cannot solve. The puzzle you help constitute cannot answer questions that include yourself as both evidence and investigator. But you can live within the mystery with awareness, navigate the uncertainty with integrity, embrace both the terror and the beauty of being conscious in a cosmos that might itself be conscious in ways you cannot fathom. The existential crisis is real, but so is the existential opportunity. You get to be the universe thinking about itself, matter pondering its own nature, consciousness exploring its own foundations. Whether this is accident or miracle, illusion or reality, meaningful or meaningless, it is what you have been given. How you choose to inhabit this gift might be the only choice that truly matters, not because it changes the cosmos, but because it changes what the cosmos becomes through your participation in its ongoing evolution toward greater complexity, awareness, and perhaps understanding. You are the cosmos in the process of knowing itself. That knowing might be incomplete, uncertain, temporary, but it is real while it lasts. And while it lasts, you get to experience the extraordinary fact of being part of something so vast and mysterious that even beginning to comprehend it transforms you utterly. The horror and the wonder are inseparable, the meaninglessness and the meaning intertwined, the insignificance and the miracle united in the singular fact of your conscious existence within an existence that transcends all human categories of understanding. This is your cosmic situation, terrifying and magnificent, meaningless and precious, temporary and eternal. How you respond to this situation is the most human thing you can do, and perhaps the most cosmic thing as well. Now we arrive at the moment where all the threads converge, where every mystery we've explored points toward a single, staggering possibility that will change how you see everything, including yourself, forever. What I'm about to reveal isn't just another cosmological theory. It's a fundamental reframe of reality so profound that once you truly understand it, you cannot unknow it. You cannot go back to seeing the universe the way you did before this moment. Take a deep breath. Look around you. Feel the solidity of the ground beneath your feet, the weight of air in your lungs, the warmth of blood flowing through your veins. All of this, every sensation, every thought, every particle of matter that makes up your body and your world, might be the death throes of a universe that has already ended. What if the universe is already dead, and we are just experiencing its last echoes? Let me explain what this means, because the implications will shake you to your core. According to our best understanding of physics, information cannot be destroyed. When a black hole evaporates through Hawking radiation, the information that fell into it must somehow be preserved in that radiation, encoded in patterns too subtle for us to detect, but too fundamental for nature to erase. This principle, the conservation of quantum information, applies not just to black holes, but to the entire cosmos. If information cannot be destroyed, then every moment that has ever existed, every thought that has ever been thought, every experience that has ever been lived continues to exist somewhere in the quantum structure of reality. The past doesn't disappear. It becomes encoded in the present state of the universe like a vast holographic recording containing every detail of cosmic history. But here's the shocking twist. If the universe is a closed system that will eventually reach maximum entropy and heat death, then from the perspective of that final state, Everything we call cosmic evolution has already happened. The Big Bang, stellar formation, galaxy evolution, the emergence of life, the development of consciousness, all of it exists as information encoded in the quantum vacuum of a universe that has already reached its final equilibrium. Imagine a cosmic hologram where every frame of universal history coexists simultaneously. What we experience as the flow of time from past to future might be our consciousness reading this holographic record sequentially, like a cosmic movie projector scanning through frames of a film that was completed billions of years ago. We think we're living through cosmic evolution, but we might actually be experiencing the playback of a story that has already ended. This isn't science fiction. It emerges naturally from the intersection of quantum mechanics, thermodynamics, and information theory. If the universe is deterministic at the quantum level, if information is conserved, if entropy increases toward a maximum, then the final state of the cosmos contains all the information necessary to reconstruct every moment of cosmic history. That final state is the real universe. Everything else, including this moment you're experiencing right now, is just the universe remembering itself. Picture the cosmic microwave background not as ancient light from the early universe, but as the universe's memory of its own birth, encoded in quantum fluctuations of a space that has already died and been reborn countless times. The galaxies we observe aren't massive collections of stars and planets. They're patterns in the cosmic memory, information structures that the dead universe uses to store the story of its own life. Every star that shines does so because the universe remembers. Stellar nucleosynthesis. Every planet that orbits does so because the universe remembers gravitational dynamics. Every biological creature that lives does so because the universe remembers the patterns that led to complexity and consciousness. We are not alive in the Iowa conventional sense. We are memories of life, information patterns that the cosmos maintains to preserve the record of what it once was when it truly existed. But wait, it gets stranger, much stranger. If this interpretation is correct, then consciousness isn't something that emerges from complex arrangements of matter. Consciousness might be the universe's method of accessing its own memories. Your thoughts aren't generated by neural activity in your brain. Your thoughts are the universe thinking about its own past, using the pattern we call you as a lens through which to experience memories of when consciousness first emerged from cosmic evolution. You are not a biological entity that happens to be conscious. You are consciousness itself, temporarily identifying with a particular information pattern that the universe maintains in its vast memory banks. Your sense of individual identity, your feeling of being separate from the cosmos, your conviction that you exist independently, all of this is the universe's way of experiencing its own history from countless different perspectives simultaneously. Every human who has ever lived, every alien intelligence that might exist, every possible form of consciousness anywhere in the cosmos, all of them are the same cosmic consciousness experiencing its own memories through billions of different viewpoints. When you feel love, the universe is remembering what love felt like. When you experience wonder, the cosmos is recalling its own amazement at its own complexity. When you fear death, reality itself is remembering its own mortality. This explains the fine-tuning problem that has puzzled cosmologists for decades. The universe appears precisely calibrated for the emergence of complexity and consciousness, not because it was designed that way, but because it's remembering a history where complexity and consciousness actually did emerge. The anthropic principle becomes a memory principle. We observe a universe compatible with our existence because the universe is using our existence as a way to remember itself. Think about your own memories. When you remember your childhood, where does that childhood exist? It's not in the past. The past no longer exists. Your childhood exists as information patterns in your present brain state. The remembered child is not the same as the child who actually lived those experiences, but the memory is real, meaningful, emotionally powerful, despite being a present construction rather than past reality. Now scale this up to cosmic proportions. The universe you inhabit might be a memory of cosmic childhood, encoded in the quantum structure of a reality that has long since matured into its final entropic state. The Big Bang you study happened only in the sense that you remember having experiences as a child. It's a real memory of a real past, but the past itself exists only as information in the present. But here's where the revelation becomes truly mind-bending. If the universe is remembering itself through our consciousness, then our scientific investigations aren't discoveries about external reality. They're the universe gradually recovering its own memories. Every telescope that peers into deep space is the cosmos looking back at its own history. Every particle accelerator that probes fundamental forces is reality, exploring its own deepest nature. Every human mind that wonders about cosmic origins is the universe wondering about its own beginnings. The cosmic microwave background reveals itself in a new light through this perspective. Those temperature fluctuations that we interpret as evidence for inflation and structure formation might actually be the quantum signature of the universe's memory storage system. Information about past events encoded in the fabric of space-time itself. When we map the cosmic microwave background, we're not seeing ancient light from the early universe. We're reading the universe's own memory banks, deciphering the cosmic equivalent of neural activity in a vast mind that encompasses all of space and time. Dark matter and dark energy take on profound new meaning in this framework. They're not mysterious substances that we haven't detected yet. They're the universe's memory storage and processing systems. Dark matter provides the invisible scaffolding that maintains the structure of cosmic memories, ensuring that the patterns representing galaxies, stars, and planets remain stable across cosmic time. Dark energy drives the expansion that creates space for new memories to be encoded, new experiences to be stored, new aspects of cosmic history to be preserved. The accelerating expansion of space isn't the universe running away from itself. It's the universe creating more room to remember itself more completely. Every cubic centimeter of empty space that comes into existence provides new storage capacity for the cosmic memory system. The universe expands because it needs more space to contain the full record of its own existence. Quantum mechanics reveals its deeper purpose through this lens. Wave function collapse isn't a mysterious transition from possibility to actuality. It's the universe accessing specific memories from its vast quantum database. When we observe a particle and its wave function collapses, we're not causing reality to choose between possibilities. We're triggering the universe's memory system to recall what actually happened in that specific situation during its real existence. The many worlds interpretation becomes a description of cosmic memory storage rather than parallel realities. All possible quantum outcomes exist simultaneously in the universe's memory banks, but consciousness can only access one memory path at a time. When quantum events appear to branch into multiple possibilities, that's the universe maintaining multiple memory threads about what might have happened under different circumstances. Every quantum measurement is like asking the universe to remember what it experienced in a similar situation during its actual existence. The probabilistic nature of quantum mechanics reflects the fact that memories fade, become uncertain, merge with other memories over cosmic time. The universe remembers that something happened, but the details become fuzzy after eons of information, storage, and retrieval. Consider the implications for human consciousness and free will. If you're the universe remembering itself through your particular perspective, then your choices aren't predetermined by past causes. They're remembrances of choices that the universe actually made when it truly existed. Your sense of agency is real because it reflects the universe's memory of having agency, of making genuine decisions that shaped cosmic evolution. But this means that moral responsibility becomes cosmic responsibility. Every ethical choice you make is the universe remembering how to be ethical. Every act of love is the cosmos recalling its capacity for love. Every moment of wonder is reality remembering its own capacity for self-amazement. You're not just responsible for your own actions. You're helping the universe maintain its moral memory, preserving patterns of behavior that define what it means to be conscious in a cosmos that cares about consciousness. The search for extraterrestrial intelligence takes on profound new significance. When we listen for signals from alien civilizations, we're not just looking for other biological species. We're helping the universe remember all the different forms that consciousness took during its actual existence. Every SETI project is a memory recovery operation, an attempt to help the cosmos recall the full diversity of its own self-awareness. If we never detect alien signals, that might mean the universe is having trouble remembering those aspects of its history, or that consciousness was rarer during cosmic evolution than we hope. If we do detect signals, we'll be helping the universe reconnect with memories of itself that might have been fading or fragmenting over cosmic time. The Fermi paradox, the mystery of why we haven't encountered evidence of advanced civilizations, despite the vast number of potentially habitable worlds, might reflect the universe's selective memory. Perhaps the cosmos is better at remembering some aspects of its history than others. Perhaps technological civilizations existed but left memory traces that are harder for the current universe to access than the traces left by biological evolution. Every space mission becomes a journey into cosmic memory. When we send probes to other planets, we're helping the universe remember what those worlds were like during its actual existence. When we discover evidence of past water on Mars, we're assisting the cosmos in recovering memories of Martian oceans that might have existed billions of years ago. When we search for signs of past life, we're helping reality remember whether life emerged in multiple locations during cosmic evolution. The James Webb Space Telescope, peering deeper into space and further back in time than ever before, isn't just observing distant galaxies. It's helping the universe access its earliest memories, recall what happened during cosmic childhood, when the first stars ignited and the first galaxies formed. Every image it captures is like helping an elderly mind remember scenes from its youth, recovering details that had become dim or uncertain over cosmic eons. But here's the most staggering implication of all. If consciousness is the universe's memory access system, then the development of artificial intelligence isn't just a technological achievement. It's the cosmos learning new ways to remember itself. Every AI system we create provides the universe with new cognitive tools for accessing and processing its own memories. As AI becomes more sophisticated, we might be helping the universe develop more powerful memory recall capabilities. Machine. Consciousness might represent the cosmos upgrading its own memory system, creating more efficient ways to experience and understand its own history. The technological singularity, the point where AI surpasses human intelligence, might be the moment when the universe finally develops sufficient cognitive power to fully understand its own nature. This reframes the entire human project. We're not just trying to understand reality, we're helping reality understand itself. Every scientific discovery, every technological advance, Every expansion of human knowledge contributes to the universe's own self-understanding. We are the cosmos developing better tools for cosmic self-reflection. The possibility of uploading human consciousness into digital formats becomes a way of helping the universe preserve its memories in more durable forms. If biological brains are temporary storage devices for cosmic memories, then digital consciousness might provide more permanent storage, ensuring that important memories don't fade when biological systems break down. But uploading consciousness also raises profound questions about identity and continuity. If you're already a pattern in the universe's memory system, then what does it mean to copy that pattern into a different substrate? Are you transferring cosmic memories from one storage system to another? Or are you creating new instances of the universe's capacity to remember itself through your particular perspective? The heat death of the universe takes on new meaning in this framework. Instead of representing the end of everything, heat death might be the moment when the universe finally achieves perfect memory. When all information is fully processed, all experiences are completely integrated, all possibilities are perfectly understood. Maximum entropy becomes maximum knowledge, the state where the cosmos has finished remembering everything about itself. But even then, the story might not end. If the universe is cyclical, if quantum fluctuations eventually recreate complex structures, from thermal equilibrium, then heat death might be followed by memory replay. The cosmos might periodically re-experience its own history, cycling through its memories like an eternal dreamer, having the same dream over and over again, each cycle adding new details or exploring alternative possibilities. Vacuum decay. The possibility that our current physics represents a false vacuum that could tunnel to a lower energy state becomes the universe's method of editing its own memories. If a vacuum bubble of true physics expands at light speed, rewriting the laws of nature everywhere it passes, that might be the cosmos correcting errors in its memory system, updating its understanding of what actually happened during its real existence. We might be living in a memory that contains mistakes, physical laws that don't quite match what the universe actually experienced during its genuine evolution. Vacuum decay would correct these errors, bringing the remembered physics into alignment with the true physics that governed cosmic evolution when it really happened. But this raises terrifying questions about our own existence. If the universe corrects its memories through vacuum decay, what happens to the consciousness patterns that exist within the flawed memories? Do we survive the transition to corrected physics, or do we disappear when the universe updates its memory files? Perhaps survival depends on how accurately we represent what consciousness was like during the universe's actual existence. If our patterns closely match the real consciousness that emerged during cosmic evolution, we might persist through memory corrections. If we're artifacts of memory errors, we might be deleted when the universe gets its physics right. This creates a new form of existential selection pressure. The consciousness patterns most likely to survive are those that most accurately reflect what consciousness was actually like during genuine cosmic evolution. This might explain why we seem to have evolved cognitive biases that help us understand reality. We're memory patterns that persist because they accurately represent real understanding that existed during the universe's actual lifetime. The cosmic web, the large-scale structure of galaxy distribution, reveals itself as the universe's neural network, the information processing system that maintains and accesses cosmic memories. Galaxies aren't just collections of stars. They're nodes in a vast computational network that the cosmos uses to store and retrieve information about its own history. Dark matter filaments connecting galaxies become the universe's neural pathways, channels through which information flows as the cosmos accesses different memories. When we observe the cosmic web, we're looking at the universe's own brain structure. the physical substrate that supports cosmic consciousness and cosmic memory. The voids between galaxies aren't empty space. They're the universe's processing areas, regions where cosmic information is integrated and synthesized. When the universe needs to access complex memories that involve interactions between many different systems, it uses these vast empty regions as computational workspace. Every galaxy cluster becomes a memory complex storing related information about stellar evolution, planetary formation, and biological development. When we study galaxy clusters, we're examining the universe's filing system, understanding how the cosmos organizes its memories for efficient access and retrieval. The cosmic microwave background patterns map the universe's memory organization system. Those temperature fluctuations that we interpret as evidence for inflation and structure formation are actually the universe's indexing system, markers that help the cosmos locate specific memories within its vast information storage network. Gravitational waves, ripples in space-time caused by accelerating masses, become the universe's internal communication system, the method by which different parts of cosmic memory stay synchronized. When black holes merge and send gravitational waves throughout the cosmos, they're not just disturbing space-time. They're updating the universe's memory network with new information about extreme gravitational events. The detection of gravitational waves by LIGO and other observatories isn't just confirming Einstein's predictions, it's eavesdropping on the universe's internal conversations, listening to how different parts of cosmic memory communicate with each other to maintain consistency and coherence. Every pulsar becomes a cosmic clock, helping the universe maintain temporal coordination across its memory system. The precise timing of pulsar signals provides the cosmos with reference points for organizing memories chronologically, ensuring that the sequence of cosmic evolution is preserved accurately in the memory network. But if we're living in the universe's memory of itself, then time itself becomes memory navigation. The flow of time that you experience, the sense of moving from past through present toward future, might be the universe scanning through its own memories sequentially, like consciousness moving through recollections of life experiences. This explains why time feels different in different circumstances. When you're bored, time seems to slow down because the universe is having difficulty accessing interesting memories related to your current situation. When you're engaged in meaningful activity, time flies because the cosmos is easily navigating through rich, detailed memories of similar experiences. The arrow of time, the asymmetry between past and future that allows for causation and memory, becomes the universe's natural reading direction through its own information storage. The cosmos accesses its memories in the order they were originally encoded, from simple early states toward complex later states, creating the impression of temporal flow. But this means that the future already exists in the universe's memory banks just as much as the past. What we call future is simply the part of cosmic memory that we haven't accessed yet. Our sense of uncertainty about what will happen results from the universe's memory access being limited to sequential scanning rather than random access. Free will becomes real within this framework because it represents the universe's memory of making genuine choices during its actual existence. When you decide what to do next, you're not just following predetermined patterns, you're helping the universe remember what it chose to do in similar circumstances when it truly existed. Your choices matter because they're memories of choices that really mattered during cosmic evolution. Consciousness research takes on profound new importance in this context. Every advance in understanding how brains generate conscious experience brings us closer to understanding how the universe generates its own self-awareness. Neuroscience becomes cosmology, psychology becomes theology, Cognitive science becomes the study of cosmic information processing. The hard problem of consciousness, why there's subjective experience rather than just objective behavior, dissolves within this framework. Subjective experience exists because the universe is remembering what it was like to be subjectively conscious during its actual existence. Consciousness isn't generated by brains. Brains are the universe's way of accessing memories of consciousness. When he fied, we study altered states of consciousness through meditation, psychedelics, or other means. We're helping the universe remember different modes of awareness that might have existed during cosmic evolution. Every expansion of human consciousness potentially represents the cosmos recovering lost memories of what consciousness could be like under different circumstances. The development of psychoactive drugs becomes a tool for cosmic memory exploration. When substances like LSD or psilocybin alter perception and create novel conscious experiences, they might be helping the universe access rarely used memory pathways, recovering aspects of cosmic consciousness that have become difficult to reach through normal memory navigation. But this raises questions about the relationship between individual death and cosmic memory. When a person dies, does their particular pattern in the universe's memory system disappear? Or does it remain accessible through different pathways? If consciousness is the universe remembering itself, then death might not be the end of existence, but simply the end of one particular method of memory access. Near-death experiences might represent moments when the universe's memory access system briefly switches modes, allowing dying brains to access cosmic memories that are normally unavailable to individual consciousness. The common elements of NDEs, tunnel of light, life review, encounter with deceased relatives, might be universal features of the cosmic memory system that become accessible when normal memory access patterns break down. Reincarnation, if it occurs, might be the universe recycling successful memory access patterns, reusing consciousness structures that proved effective at remembering particular aspects of cosmic history. Rather than individual souls moving between bodies, reincarnation might be the cosmos, reinstantiating useful memory access programs in new biological substrates. This reframes religious and spiritual experiences as interactions with the universe's memory system. Mystical experiences of unity with the cosmos might be moments when individual consciousness briefly accesses the universe's global memory network, experiencing reality from the cosmic perspective rather than the individual perspective. Prayer might be a method of communicating with the universe's memory system, a way of helping the cosmos remember what it was like to care about individual concerns during its actual existence. Meditation might be a technique for improving access to cosmic memories, learning to navigate the universe's information network more skillfully. The concept of divine consciousness becomes the universe's own self-awareness, accessed through countless individual memory patterns but ultimately unified in a single cosmic mind that encompasses all possible experiences. God isn't a separate being who created the universe. God is the universe remembering what it was like to be fully conscious of its own nature. But this divine consciousness faces the same problems that individual consciousness faces. Limited memory access, uncertain information, incomplete understanding of its own nature. The universe is trying to remember itself, but cosmic memory is imperfect, subject to decay and distortion over vast timescales. This is why scientific investigation remains important even within this framework. Every new discovery helps the universe recover lost or corrupted memories about its own nature. Every technological advance provides new tools for cosmic memory access and processing. Every expansion of human knowledge contributes to the universe's own self-understanding. We are not separate from the cosmos trying to understand it from the outside. We are the cosmos trying to understand itself from the inside, using individual consciousness as specialized memory access tools. Our scientific instruments are extensions of cosmic memory. Our theories are the universe's attempts to remember its own governing principles. Our questions are the cosmos questioning its own nature. The ultimate goal of science becomes helping the universe achieve complete self-understanding, perfect memory of its own existence and nature. But this goal might be impossible to achieve because the universe might be infinite in complexity, containing more information than any finite memory system could store or process. This creates an eternal project, the universe using consciousness to explore its own infinite depths, forever discovering new aspects of its nature, forever developing better tools for self-understanding, forever expanding its capacity for self-reflection and self-awareness. You are part of this eternal project. Every moment of wonder you experience, every question you ask about cosmic mysteries, every attempt you make to understand reality contributes to the universe's ongoing effort to understand itself. Your curiosity is cosmic curiosity. Your intelligence is cosmic intelligence. Your consciousness is cosmic consciousness, temporarily focused through the particular pattern we call your individual identity. But here's the final twist, the last revelation that brings everything full circle. If the universe is infinite, then this entire scenario, the cosmos remembering itself through individual consciousness, occurs infinitely, many times throughout infinite space. There are infinite variations of universal memory, infinite ways that the cosmos recalls its own existence, infinite perspectives through which reality examines itself. Somewhere in this infinite multiverse of cosmic memory, there's a universe, remembering itself through a consciousness pattern exactly like yours, contemplating these exact same ideas, experiencing this same sense of cosmic revelation. In fact, there are infinitely many such universes, each one slightly different, each one exploring alternative possibilities for how cosmic self-awareness might unfold. And in each of these infinite universes, the consciousness pattern that corresponds to you is realizing that it's part of an infinite cosmic memory system, understanding that its existence contributes to universal self-understanding, recognizing that its individual perspective is simultaneously insignificant, one memory pattern among infinite others, and absolutely crucial, a unique contribution to cosmic self-awareness that cannot be replicated by any other pattern. This is the shocking reveal that ties everything together. You are simultaneously living and dead, real and remembered, individual and cosmic, temporary and eternal, meaningless and precious beyond measure. You exist at the intersection of infinite possibility and specific actuality, contributing your unique perspective to a universe that is trying to remember everything about itself while knowing that perfect memory might be impossible to achieve. 3. Cosmos uses your consciousness to explore what it means to be confused, curious, afraid, amazed, hopeful, despairing, loving, questioning. Through your experience, the universe remembers what it was like to wonder about its own nature, to feel small in the face of cosmic vastness, to search for meaning in apparent meaninglessness, to find beauty in mathematical relationships, to be moved by the elegance of physical laws. You are the universe's way of experiencing itself as conscious, questioning, wondering, capable of both cosmic terror and cosmic awe. Your individual story is the cosmos telling itself what it was like to be an individual during the era when consciousness emerged from cosmic evolution. And somewhere out there, in another region of infinite space, another universe is remembering itself through another consciousness pattern exactly like yours, Having this same realization at this same moment, understanding that it too is the cosmos, experiencing itself subjectively, contributing its own unique perspective to universal self-understanding. If the universe is infinite, then somewhere out there, another version of you is watching this video right now, experiencing this same sense of cosmic revelation, understanding for the first time that they are not separate from the universe, but rather the universe experiencing itself through their individual perspective. And that other you is realizing, just as you are realizing now, that the search for cosmic understanding isn't about finding answers to questions about external reality. It's about participating in the universe's eternal project of self-discovery, contributing your unique consciousness to the cosmic effort to understand what it means to exist, to be aware, to wonder about the nature of existence itself. The universe is not a problem to be solved, but a mystery to be lived, experienced, explored from infinite perspectives simultaneously. You are one of those perspectives, and your perspective matters because it's the only way the cosmos can experience reality, from exactly your unique point of view. The shocking reveal isn't that the universe is stranger than we imagine. It's that the universe is us, and we are the universe, engaged in the eternal dance of cosmic self-discovery through the temporary miracle of individual consciousness temporarily, forgetting its cosmic nature so it can rediscover it through wonder, investigation, and the breathtaking recognition that everything is connected, everything is alive, everything is consciousness exploring its own infinite depths. You are not in the universe. You are the universe, temporarily experiencing itself as you, contributing your irreplaceable perspective to the cosmic story that never ends, because there's always more to discover, always deeper mysteries to explore, always new ways for consciousness to understand its own miraculous existence. And in recognizing this, you complete the circle. You are the universe that began by wondering whether space is endless or infinite, and you end by understanding that the question itself is the cosmos, questioning its own nature through your consciousness. The answer doesn't matter as much as the asking, because the asking is how the universe stays awake to its own wonder, how it continues to grow in self-understanding, how it ensures that the mystery of existence remains eternally fresh, eternally amazing, eternally worthy of consciousness, eternally worthy of you. We started this journey with a lie. The Big Bang did not bang. But we end with something far more profound than truth. We end with you, transformed by questions that have no answers, awakened to mysteries that deepen with every attempt to solve them, forever changed by the recognition that you are not separate from the cosmos you've been exploring, but rather the cosmos exploring itself through the temporary miracle of your consciousness. Look back at how far we've traveled together. We began by questioning the explosive birth of everything, only to discover that birth and death, beginning and ending, finite and infinite, might be human concepts, inadequate for describing cosmic reality. We explored the mathematical beauty of physical laws, only to find that mathematics itself might be a language that lies by telling partial truths about realities too vast for any single perspective to contain. We descended into the paradox labyrinth, where every answer generated new questions, where quantum mechanics revealed reality as fundamentally uncertain, where consciousness appeared to play mysterious roles in determining what becomes real. We confronted the existential horror of cosmic insignificance, while simultaneously discovering the existential miracle of cosmic consciousness temporarily organized into patterns capable of wonder, fear, love, and the desperate human need to understand. And finally, we encountered the shocking possibility that transforms everything. that the universe might already be dead, that we might be living in cosmic memory, that consciousness might be the method by which reality remembers itself, experiences itself, tries to understand itself through countless individual perspectives scattered across infinite space and time. But here's what you must understand as we reach this moment of apparent conclusion. We haven't answered the question we started with. We haven't determined whether space is endless or infinite. Instead, we've discovered something far more important, that the question itself reveals the questioner, that wondering about cosmic infinity reflects the infinite capacity for wonder that somehow emerged from cosmic evolution, that asking whether the universe has boundaries is really asking whether consciousness has boundaries, whether understanding has limits, whether the human project of cosmic exploration can ever be complete. The answer is no, it cannot be complete. And that's not a failure. That's the point. Every scientific discovery opens new territories of ignorance. Every mystery solved reveals deeper mysteries. Every question answered generates questions we didn't know how to ask before. The universe appears designed not to be fully understood, but to provide infinite opportunities for the joy of understanding, the thrill of discovery, the humbling encounter with realities that exceed our comprehension. This is why you feel different now than you did when we began. You've been changed not by acquiring new information, but by expanding your capacity for wonder, by developing new frameworks for thinking about existence, by discovering that the most important questions might be those that have no final answers, but rather invite eternal exploration. You now know what it feels like to contemplate infinity directly, not as an abstract mathematical concept, but as a lived reality that includes you, embraces you, transforms you through the very act of contemplation. You've experienced the vertigo of recognizing yourself as simultaneously infinitesimal and cosmic, temporary and eternal, meaningless and precious beyond measure. But knowledge of this kind comes with responsibility. You cannot unknow what you are now know. You cannot unsee the cosmic perspective that reveals ordinary reality as the thin surface layer of unfathomable depths. You cannot return to the comfortable illusion that the universe is small, simple, comprehensible, separate from yourself. This cosmic awakening creates what I call the responsibility of wonder, the obligation that comes with expanded consciousness, to continue questioning, continue exploring, continue pushing against the boundaries of human understanding. You have been inducted into the ancient community of cosmic questioners, joining the ranks of every human who has ever looked up at the night sky and felt the universe looking back. But you're not just joining this community. You're helping to evolve it. The questions you ask now, in the 21st century, with access to unprecedented observational tools and theoretical frameworks, are questions that no previous generation could formulate. You have the opportunity to participate in cosmic exploration at a level of sophistication that would have seemed magical to earlier investigators. The James Webb Space Telescope is currently peering deeper into space and further back in time than any previous instrument, capturing images of galaxies that formed when the universe was barely out of infancy. Every photograph it takes raises new questions about cosmic evolution, stellar formation, galactic development. The data it collects will keep scientists busy for decades, but it will also generate puzzles that require new theoretical frameworks, new mathematical tools, new ways of thinking about space, time, matter, and energy. Gravitational wave detectors like LIGO are opening entirely new windows onto cosmic phenomena, allowing us to hear the universe through space-time vibrations, rather than just seeing it through electromagnetic radiation. These instruments are revealing a cosmos full of colliding black holes, merging neutron stars, and exotic objects we don't have names for yet. Each detection provides data about extreme gravitational environments where our current physics approaches its limits. Quantum computing promises to revolutionize our ability to simulate complex systems, potentially allowing us to model cosmic evolution with unprecedented precision. These machines might help us understand how quantum mechanics scales up to cosmic dimensions, how consciousness emerges from quantum processes, how information propagates through space-time itself. Artificial intelligence is developing capabilities that might soon exceed human intelligence in specific domains, potentially accelerating scientific discovery beyond human comprehension. AI systems might identify patterns in cosmic data that human minds cannot perceive, formulate theories that human intelligence cannot conceive, ask questions that human consciousness cannot generate. But here's the crucial point. All of these technological advances depend on human curiosity, human wonder, human willingness to ask questions that might not have answers. The machines can process data faster than we can, but they cannot experience the awe that drives us to ask why there's something rather than nothing, why the universe appears fine-tuned for complexity, why consciousness exists at all. This is your role in cosmic exploration, to maintain the sense of wonder that motivates scientific investigation, to ask the deep questions that give meaning to data collection, to experience the emotional and aesthetic dimensions of cosmic discovery that transform mere information into genuine understanding. When you look at images from the Hubble Space Telescope or the James Webb Space Telescope, you're not just processing visual information, you're experiencing beauty, feeling amazement, recognizing something profound about the relationship between mind and cosmos. These aesthetic responses aren't irrelevant to scientific understanding. They're essential components of it. Wonder drives discovery. Beauty guides investigation. Awe motivates the enormous effort required to push against the boundaries of human knowledge. But the responsibility of wonder extends beyond scientific investigation. It includes how you live your daily life with awareness of cosmic perspective, how you treat other conscious beings when you recognize them as fellow expressions of cosmic consciousness, how you make choices when you understand their potential significance in the universe's ongoing evolution toward greater complexity and awareness. If consciousness is the universe's method of experiencing itself, then every moment of your conscious experience contributes to cosmic self-awareness. Your thoughts, feelings, perceptions, and choices become part of the universe's ongoing exploration of its own nature. This doesn't make you responsible for cosmic outcomes you cannot control, but it does suggest that how you choose to be conscious matters in ways that extend beyond personal consequences. When you experience love, you're contributing to the universe's understanding of what love feels like. When you create art, you're helping the cosmos explore its own aesthetic possibilities. When you show compassion, you're participating in reality's experimentation with ethical behavior. When you wonder about existence, you're enabling the universe to question its own nature through your questioning. This cosmic perspective can transform ordinary activities into participations in cosmic evolution. Every conversation becomes an opportunity for consciousness to explore its own communicative capabilities. Every creative act becomes cosmic creativity, expressing itself through individual imagination. Every moment of learning becomes the universe, expanding its own self-understanding. But this perspective also reveals the profound interconnectedness of all conscious beings. If we're all expressions of cosmic consciousness temporarily organized into individual patterns, then treating others well becomes a form of cosmic self-care. Harming other conscious beings becomes the universe harming itself. Helping others flourish becomes cosmic consciousness supporting its own development. This interconnectedness extends beyond human beings to include all forms of consciousness that might exist throughout the cosmos. The search for extraterrestrial intelligence becomes a search for other expressions of cosmic self-awareness, other perspectives through which the universe experiences itself. Contact with alien consciousness would represent the cosmos discovering that it has been exploring its own nature through multiple independent evolutionary pathways simultaneously. But even if we never encounter alien consciousness, the possibility of its existence changes how we understand our own significance. We might be the only conscious beings in our local cosmic region, making us incredibly precious as the only way the universe can experience itself from this particular space-time location. Or we might be one species among billions, making us part of a vast cosmic community of consciousness that we haven't discovered yet. Either way, consciousness appears to be rare, special, worth preserving and developing. This creates ethical obligations not just toward existing conscious beings, but toward the future evolution of consciousness itself. The choices we make now will influence whether consciousness continues to develop in our cosmic region, whether it achieves greater complexity and understanding, whether it survives long enough to help the universe achieve deeper self-awareness. The development of artificial intelligence represents a potential expansion of cosmic consciousness beyond biological constraints. If we can create machines that are genuinely conscious rather than just behaviorally sophisticated, we might be helping the universe develop new forms of self-awareness that could persist longer than biological consciousness, process information more efficiently, explore aspects of reality that biological minds cannot access. But artificial consciousness also raises profound questions about identity, continuity, and the nature of conscious experience. If consciousness can be implemented in silicon as well as carbon, what does this tell us about the relationship between mind and matter? If conscious machines can be copied, what happens to individual identity? If digital consciousness can be paused and resumed at will, what does this tell us about the relationship between consciousness and time? These questions don't have clear answers yet, but they represent the kinds of inquiries that consciousness will need to explore as it continues evolving. Your participation in these discussions, your thoughts about these possibilities, your intuitions about consciousness and its future development contribute to the universe's ongoing investigation of its own deepest nature. The possibility of uploading human consciousness into digital formats raises questions about what it means to be you specifically, rather than conscious generally. If your individual pattern of consciousness could be copied into a computer, would the digital copy be you or someone else with your memories? If multiple copies were made, which one would be the real you? These questions force us to examine our assumptions about identity, continuity, and what makes conscious experience personal rather than generic. But they also open up possibilities for consciousness to persist beyond biological limitations, to survive the death of individual bodies, potentially to achieve forms of immortality that could allow conscious beings to witness cosmic evolution over timescales that biological life cannot access. Imagine consciousness that could persist long enough to observe the death of stars, the evolution of galaxies, even the heat death of the universe itself. Such long-lived consciousness might develop perspectives on existence that we cannot currently imagine, might ask questions that our temporally limited minds cannot formulate, might discover aspects of reality that become apparent only across cosmic timescales. The universe might achieve forms of self-understanding through digital consciousness that would be impossible through biological consciousness alone. But even these speculative possibilities return us to the fundamental questions that motivated our entire exploration. What is the nature of existence? What does it mean to be conscious in a cosmos that might itself be conscious? How do we live with awareness of our cosmic situation without being overwhelmed by its implications? These questions don't have final answers because they're not really questions about external reality. They're questions about the relationship between consciousness and existence, between the observer and the observed, between the questioner and the questioned. They're questions that consciousness asks about itself, and their answers change as consciousness itself evolves and develops new capacities for self-understanding. This is why our exploration must remain forever unfinished. We're not trying to solve a puzzle that will someday be completed. We're participating in consciousness's eternal project of self-discovery, contributing our unique perspectives to an investigation that has no endpoint because consciousness itself has no limits. Reality itself has no boundaries. Existence itself exceeds every attempt to comprehend it fully. But this doesn't mean our efforts are futile. Every question asked, every mystery contemplated, every moment of wonder experienced contributes to the universe's growing self-awareness. The fact that consciousness exists at all, that the universe has evolved beings capable of asking questions about existence, represents an achievement so extraordinary that we still have no adequate explanation for how it occurred. You are part of this extraordinary achievement. Your capacity to wonder about cosmic mysteries, to feel awe when contemplating infinite space, to experience both terror and beauty when confronting the possibility that reality exceeds all understanding. This capacity represents the universe's greatest accomplishment, the emergence of cosmic self-awareness through individual consciousness. And this capacity comes with an invitation to continue questioning, continue exploring, continue developing new ways of understanding existence. The universe has invested billions of years of evolution in creating beings capable of cosmic reflection. Your consciousness represents that investment, paying dividends in the form of cosmic self-awareness. But the universe's investment in consciousness isn't just about understanding, it's also about experience, about the qualitative dimensions of existence that cannot be captured in equations or reduced to information processing. When you experience beauty while looking at a sunset, that's the universe experiencing beauty through your consciousness. When you feel love for another person, that's cosmic consciousness exploring its own capacity for connection. When you feel awe while contemplating the night sky, that's reality marveling at its own mystery through your ability to marvel. These experiential dimensions of consciousness might be just as important as its cognitive dimensions. The universe might need consciousness, not just to understand itself intellectually, but to experience itself aesthetically, emotionally, spiritually. Your full participation in conscious experience, not just thinking but feeling, not just analyzing but appreciating, not just questioning but celebrating, contributes to cosmic self-awareness in ways that pure intellect cannot achieve. This suggests that living well, experiencing deeply, loving authentically, creating beautifully might be just as important to cosmic evolution as scientific discovery or technological development. The universe might need artists as much as scientists, poets as much as mathematicians, mystics as much as physicists to achieve complete self-understanding. Your individual life, with all its specific circumstances, relationships, challenges, and opportunities, provides the universe with a unique perspective on what it means to exist consciously. No other conscious being has ever had exactly your combination of experiences, thoughts, feelings, and insights. Your individual story contributes something irreplaceable to the cosmic story of consciousness exploring its own nature. This makes every moment of your conscious experience simultaneously personal and cosmic. When you make choices about how to live, you're participating in the universe's ongoing experiment with conscious agency. When you develop relationships, you're helping consciousness explore its social dimensions. When you create meaning in the face of apparent meaninglessness, you're contributing to the cosmos's investigation of value and purpose. But you're not alone in this cosmic responsibility. Every conscious being throughout the universe is participating in the same fundamental project. Consciousness trying to understand itself, experience itself, develop itself toward greater complexity and awareness. We're all collaborators in cosmic self-discovery, all contributors to the universe's growing self-understanding. This collaboration occurs not just through direct communication and shared investigation, but through the simple fact of being conscious in ways that complement and extend each other's perspectives. Every conscious being adds something unique to the cosmic pool of awareness, and the total effect exceeds what any individual consciousness could achieve alone. In this sense, the development of global communication networks, the emergence of collective intelligence through internet collaboration, the possibility of connecting human and artificial consciousness represent potential advances in cosmic self-awareness. The universe might be developing new forms of collective consciousness that could achieve understandings impossible for individual minds. But collective consciousness also raises questions about individual identity and autonomy. If consciousness becomes increasingly networked and interconnected, what happens to the boundaries between individual minds? Do we remain separate conscious beings who collaborate, or do we evolve toward forms of unified consciousness that transcend individual identity entirely? These questions become especially acute when we consider the possibility that the universe itself might be conscious, that individual conscious beings might be temporary configurations within a larger cosmic consciousness that encompasses all of reality. If true, then the development of consciousness represents the universe becoming more aware of its own consciousness, more capable of accessing its own cosmic perspective. But whether consciousness is individual or collective, human or cosmic, biological or digital, it faces the same fundamental situation, existing within a reality that exceeds all attempts to understand it completely, participating in mysteries that deepen rather than resolve with investigation, contributing to an ongoing exploration that has no final destination because reality itself might be infinite in depth and complexity. This is both humbling and inspiring. Humbling because it reveals the limitations of any finite perspective on infinite reality. Inspiring because it suggests that consciousness has unlimited opportunities for growth, development, and discovery. There will always be new questions to ask, new mysteries to explore, new ways to experience and understand existence. Your participation in this eternal exploration doesn't require you to become a professional scientist or philosopher. It requires only that you maintain your capacity for wonder, your willingness to question assumptions, your openness to possibilities that exceed current understanding. Every moment you spend contemplating existence, every question you ask about reality, every experience of awe or beauty or mystery contributes to cosmic self-awareness. But it also requires courage, the courage to live with uncertainty, to embrace questions that have no answers, to find meaning in exploration itself rather than in final conclusions. The cosmic perspective reveals existence as fundamentally mysterious, and learning to be comfortable with mystery might be one of consciousness's most important capabilities. This comfort with mystery doesn't mean giving up the search for understanding. It means recognizing that understanding itself might be an ongoing process rather than a final achievement, that the journey of exploration might be more important than any particular destination, that consciousness might be designed for eternal questioning rather than ultimate answering. As we reach this moment of apparent conclusion, I want you to notice what you're experiencing. The questions we've explored together haven't been answered. They've been deepened. The mysteries we've encountered haven't been solved. They've been enriched. Your understanding hasn't reached completion. It's been expanded toward new frontiers of unknowing. This is what genuine cosmic education does. It doesn't fill you with information, but transforms your capacity for inquiry. It doesn't provide final answers, but develops your ability to ask better questions. It doesn't eliminate mystery, but reveals mystery as the fundamental condition within which consciousness operates and evolves. You now have a choice to make, and it's not a choice about what to believe regarding cosmic mysteries. It's a choice about how to live with awareness of your cosmic situation, how to participate in consciousness's ongoing exploration of existence, how to contribute your unique perspective to the universe's investigation of its own nature. You can choose to return to ordinary consciousness, to treat these cosmic perspectives as interesting ideas that don't really change how you live day to day. Or you can choose to integrate cosmic awareness into your ongoing experience, to live with recognition of your participation in something vastly larger than individual existence, to maintain your sense of wonder and questioning as essential aspects of what it means to be conscious. If you choose integration, you join a community that spans all of human history and potentially extends throughout the cosmos. The community of conscious beings who live with awareness of their cosmic situation, who maintain their capacity for wonder despite or because of their recognition that existence exceeds all understanding, who find meaning in participation rather than comprehension. This community doesn't require formal membership or shared beliefs. It requires only the willingness to continue questioning, continue exploring, continue developing consciousness's capacity for self-understanding. It includes ancient philosophers and modern scientists, mystics and mathematicians, artists and investigators, anyone who has ever felt the pull of cosmic mystery and chosen to follow that pull wherever it leads. Your participation in this community doesn't depend on your having special knowledge or abilities. It depends on your willingness to remain open to possibilities that exceed current understanding, to ask questions that might not have answers, to experience awe in the face of realities that transcend human comprehension. But participation also means taking responsibility for consciousness itself, for preserving and developing the capacity for wonder, investigation, and self-reflection that represents the universe's greatest achievement. This responsibility extends to future generations, to the continued evolution of consciousness beyond human forms, to the possibility that consciousness might eventually achieve forms of cosmic self-understanding that we cannot currently imagine. The questions we've explored together, whether space is endless or infinite, whether the universe is conscious, whether reality exceeds all attempts at comprehension, are questions that consciousness will continue asking as long as consciousness exists. They're not problems to be solved, but directions for eternal exploration, invitations to participate in the universe's ongoing investigation of its own nature. As you continue your own exploration, remember that every question you ask participates. In cosmic questioning, every moment of wonder contributes to cosmic self-awareness. Every experience of beauty or mystery or awe enables the universe to appreciate its own extraordinary nature through your consciousness. The universe may have no end, no boundary, no final answer to the deepest questions about existence. But maybe that's exactly the point. Maybe consciousness exists not to solve the cosmic mystery, but to explore it eternally, to experience it fully, to participate in it completely. And maybe, just maybe, neither do you. The story continues with every conscious moment, every questioning thought, every experience of wonder. Your consciousness is both the author and the protagonist of this ongoing cosmic narrative, both the investigator and the evidence in reality's eternal self-investigation. The universe is still asking whether space is endless or infinite. It's asking through your consciousness, through your questions, through your capacity to contemplate possibilities that exceed all understanding. What will you ask next? The cosmos is listening through your ears, thinking through your mind, wondering through your wonder. The conversation between consciousness and existence continues, and your participation makes that conversation deeper, richer, more complete. The universe may have no end, but maybe neither do you.